And welcome to the stream. It's good to be back. So, as you might know, I've been absent from YouTube for a week because of real life priorities that needed my attention. And hi, Christian. Thank you very much for joining. Welcome to the stream. It's good to be back. Oh, I can hear myself. So, okay, we'll just So this way is better. Yeah. So we will start in a few minutes. Just first of all, it's great to be back, and you guys have been awesome, and there's more content to come, obviously. Okay, so yeah, this is due to popular request. Everything is okay. Thank you very much, Christian. Yeah, so this topic is very much due to popular request because diffusion models are a hot topic right now, and a lot of people want to understand the inner working of such models. But unfortunately, understandably also, there's not a tons of accessible material on the subject. Because, first of all, it is quite a prerequisite heavy topic, the diffusion model in particular. So, and I don't think I have the prerequisite either. We'll see why that's the case. But I think I do have a substantial part of the prerequisites. So I think it will be interesting for me to attempt to understand this very powerful topic, a very powerful model. And hopefully in the process, we will make understanding this technique easier for other people as well. So this is very much a study with me session rather than a lecture. Okay, so we all have our weakness and strengths in our understanding, our background, and that's totally normal. So the ability to learn and to wonder is what matters the most. All right, so it's time. We should start the stream. And before that, I would just like to start the stream with a little bit of a prayer. Heavenly Father, we thank you for bringing us together for this study session. We thank you for the gifts of reason, curiosity, and imagination, and the creativity that you have given us. As we study the mathematics behind diffusion model, please help us remember that all these gifts ultimately come from you. Lord, please grant us not only the intelligence, but also the patience and perseverance. The mathematics before us may be difficult and at times frustrating. When we encounter concepts that we cannot immediately understand, please keep us from becoming discouraged. Give us the humility to slow down, to ask questions, to work through the details, and above all else, give us the courage to not deceive ourselves, to fake understanding. Father, we know that many people are curious about what lies underneath the modern artificial intelligence. Many want to understand how these systems work mathematically, and not just as CAN algorithms, yet accessible explanations are often difficult to find. If you allow us to gain understanding through this study, help us not to keep that knowledge to ourselves. Give us the ability and wisdom to explain these ideas clearly, so we can help others who are also seeking to understand. Thank you, Lord. You're the source of creativity and curiosity. So please help us. We are amazed by what human beings are able to create, but please also remind us that even the most advanced technology is still no match for your wisdom and your ways, as you tell us through the prophet of Isaiah. For as the heavens are higher than the earth, so are my ways higher than your ways, and my thoughts than your thoughts. So Heavenly Father, please help us be humble. Whatever we discover, whatever we learn, may it cause us to marvel more deeply at your wisdom, to appreciate and testify to your glory. And Father, we especially pray for our faith in this uncertain and difficult time. There are many things happening in this world that we cannot understand or control yet. When the future seems frightening surrounding us, please help us remember that you remain sovereign Nothing has taken you by surprise, and no amount of advancement of human technology can overturn your purpose. As we begin this study, give us clear minds, patient hearts, and humble spirit. May everything we learn tonight ultimately point beyond ourselves to your wisdom. We commit this study session into your hands. In the precious name of Jesus, our Lord and Savior, we pray. Amen. Okay, so here we have a course offered by MIT this year called Introduction to Flow Matching and Diffusion Models 2026. And it's got lecture notes, as you can see, course notes here, and slides, videos, as well as Python workbook. Python workbook. So our session is going to be mostly focused on the mathematics itself and not so much with the coding. Well, after all, this is a math channel here. And also, there's the solution set, which is also very helpful. So God bless these people, these amazing people from MIT and MIT OCW for spreading these knowledge for free. Okay, so here what we need to understand, like the bare minimum prerequisite for understand diffusion models. So let's start by reading this introductory section. Diffusion and flow models are the cutting-edge AI method for image, videos, and many other data types. This course offers a comprehensive introduction for students and researchers seeking a deeper understanding of these models. Okay, does that sound like exactly what we wanted? Lectures will teach the core mathematical concepts necessary to understand diffusion models, including stochastic differential equations and the Fokker-Planck equation. Quite luckily, actually, we just did a practical introduction to SDEs live stream, I think 2 weeks earlier. So practical introduction to SDE, we explain what an SDE mean, and in particular, the concept of Ito integrals, which is also covered in our stochastic calculus series. So if you want a more condensed version, feel free to check out the stochastic calculus series, which is by no means over, by the way. And we also derived the Fokker-Planck equation in the context of general Markov processes. Okay, so there's a separate live stream on the Fokker-Planck equation, which was the last live stream before my 1 week hiatus from YouTube. So we derived the general Fokker-Planck equation in the context of Markov processes. SDEs, in particular, Ito's SDE is a special case of continuous time Markov processes. So we actually went the hard way to derive the FP equation to develop more intuitions. Okay, so if we actually start from SDE, that would mean we would need more prerequisites, but the derivation itself would be easier. We actually went the harder route of deriving the Fokker-Planck equation from scratch. So, but we shall say something about the Fokker-Planck equation today as well. So I consider these two notions, SDEs and Fokker-Planck equation, to be my relative strong suit, so to say, if I can use that word. But I don't have much experience with generative AI methods in general. I mean, I know what I know how to, for example, derive a back propagation method, which is essentially a chain rule, but that's not really much. Okay, so that's it. Okay, so but I'm prepared to learn more about generative AI, deep generative AI in general. Perhaps that's also part of the prerequisite. Okay, and provide a step-by-step explanation to the component of each model. Labs will accompany each lecture, allowing students to gain practical hands-on experience with concept learned in a guided manner. At the end of the class, students will have built a latent diffusion model from scratch, and along the way, will gain hands-on experience with mathematical tools of stochastic analysis. That's useful in many other fields. Actually, this particular module does not assume a stochastic analysis. Okay, so you see, along the way, we'll have hands-on experience with stochastic analysis. It contains a short relatively self-contained introduction to stochastic analysis, SDEs, and Fokker-Planck. Okay, it does not assume that. This course is ideal for those who want to explore the frontiers of generative AI through a mixture of theory and practice. We recommend some prior experience with probability theory and deep learning. All right, so I think I am relatively more confident with the probability department, but not so much with the deep learning department. Okay, so I mean, this is the primary source that we will be following in this session. We will go as far as we can, okay? But there are also two extra resources. So this is the first one. This is the first one. This very webpage is the first resource I put in the description of this live stream. And there's a second source, which is a blog. Okay, so this one right here. This is a blog length treatment, if you can call it that way. Perhaps it's not necessarily reasonable to expect that we can master diffusion models simply by reading this particular blog, but at least we have a more concise overview. So this can also be helpful. Okay, so that's the second resource I listed in the description. And also there is the third one. The third one is actually a book length treatment. So this one is a new book. I mean, it's yet been published, but it's on archive. This one's called The Principle of Diffusion Model by Lai and others. Okay, which is well, amazing, right? It is a book length treatment on such a new topic. Usually, for cutting edge technologies, models like this one, like the diffusion model, the description is usually scattered in papers, among papers, and it's very difficult for non-specialists to have a self-contained development, so to say. It's difficult for outsiders to learn these models from scratch. But luckily here, there's a book. And it is quite accessible and is at the same level, I think. It's written at the same level of this course by MIT. So this is a great companion, I believe. Okay, so it has the course notes. We're mostly focusing on the course notes, but if there's additional background that we need to consult, we will try to go to this book and try to find more. Okay, and also there is a website for the book here, and it's in the archive. It's in the archive link. Supplementary material of the book are available on the book website. So this, if we click this URL, you get this website, and it's updated fairly frequently. Okay, and you can actually ask questions if you encounter specific difficulties, as far as I can tell, while you're reading. Right. So here, see, this person wonders if there's a typo here, and the author pretty much replied on the same day. Okay, so yeah, feel free to use this resource as well. Okay, so there's actually plenty of resource if you're committed to find them. Okay, so there's definitely it's something I think that is doable. Okay, not impossible. Okay, so as far as I can tell, you do not need measure theory or real analysis, hefty background in analysis to learn this course. With a little bit of a patience and consistency, standard background in calculus, linear algebra, and probability should be sufficient. All right, so let's officially get started. Okay, so let's first look at the the lecture notes. Okay, this is a lecture note from the MIT OCW. We will try to read as much as we can. And in the process, if it is heavily verbal, I will show the PDF itself. If it is mostly derivation, in a section that is mostly derivation, I'll go to my own notepad right here, just like our more typical stream. I'll do the derivation step by step. This way we actually are sure what exactly is happening. All right. Okay. Yeah, I haven't been reading the chat. Okay, but yeah, thank you everyone. Thank you everyone for tuning in. All right, so okay, so why don't we look at the first section, the first chapter, and also let us not forget there's here we have a hang on. We also have I was trying to say we also have videos. In case we run into trouble, we can also watch the video, and I'll like do a reaction on the side to see how far I can follow the lectures. I haven't watched these because I just didn't quite have the time to do the homework. Okay, so yeah, let's get started. So here, let's take a look at the lecture notes, introduction. All right, so in recent years, we have witnessed a tremendous revolution in AI. Image generators like what's that, Nano Banana and Stable Diffusion 3 can generate photorealistic and artistic images across a diverse range of styles. Okay, video models like Meta's VO3 can generate highly realistic movie clips, and large language models like ChatGPT can generate seemingly human-level responses to text prompts, and also solving mathematical mysteries too, not just regular text. Right? I'm pretty sure everyone in chat knows about the recent amazing advancement in mathematics due to AI. Okay, thank you, Ego. At the heart of this revolution lies a new ability of AI system, the ability to generate objects. While previous generations of AI systems may mainly use for prediction, these new AI systems are creative. Right? So that's this entire field of generative AI, right? Not just for predictions. Classical, traditional deep learning is like a super powerful regression model. Right? You want to approximate a function to high degrees of accuracy. Right? But now the goal here is to generate objects. They dream or come up with new objects based on user-specified input. Such generative AI systems are at the core of this recent AI revolution. All right, so the goal of this class, okay, is to teach you two of the most widely used generative AI algorithms. Okay, great. So now it's time to take notes. Two class, generative AI algorithm, denoising diffusion models and flow matching. These models are the backbones of the best image, audio, and video generation models, and have most recently became the state-of-the-art in scientific applications such as protein structures. Well, interesting. I didn't know about that. Without a doubt, understanding these models is a truly extremely useful skill to have. Okay, so why don't we write some notes here. The goal here is to learn about denoising diffusion models, try to figure out what those terminologies mean. Okay, so you have the denoising diffusion models. Okay, so that's one, and also flow matching. Okay, so these are the keywords, and these are generative models. Okay, as I said, I am very much a beginner when it comes to generative models. Okay, so we might need to do some backgrounds, like prerequisites in generative model in general. Right. So here, let's see. All of these generative models generate objects by iteratively converting noise into data. Wow, that's quite astonishing, really, because noise is seemingly contains no information, right? But somehow they can be turned into data, which raises a question of how exactly you can turn, well, chaos into pattern, and what kind of pattern you want. This evolution from noise to data is facilitated by the simulation of ordinary or SDE, all right, ordinary or stochastic differential equations. I see. So here it is talking about the numerical solutions of ordinary and stochastic differential equations. So we might need to say something about numerical analysis of ODEs and SDEs. Okay. So these are, of course, separate subjects. Okay. And I do have some experience with numerical simulations of ODE and SDE. Actually, I did my master's thesis on simulation of SDEs under boundary conditions, under various boundary conditions used in a separate field, okay, not for generative AI. But you see, it seems like it seems to me that I have some of the ingredients necessary, but I have no idea how they can be stitched together into an AI model. Okay, so flow matching and denoising diffusion models are a family of techniques that allow us to construct, train, and simulate such ODEs, SDEs at large scale with deep neural networks. Okay, interesting. So, okay, so we might need some background in deep neural networks by the looks of it. All right. While these models are rather simple to implement. Oh, interesting. These models are rather simple to implement. That's good to know. The technical nature of SDEs can make these models difficult to understand. In this course, we provide a self-contained introduction to the necessary mathematical toolbox regarding differential equations to enable you to systematically understand these models. Excellent. We then explain step by step the modern stack of the state-of-the-art image and video generators. Beyond being widely applicable, we believe that the theory behind the flow and diffusion models is elegant in its own right. Yeah, of course. Therefore, most importantly, we hope this course will be a lot of fun to you. Okay, so I think what we gain from this paragraph is that we're probably going to need numerical analysis. Numerical analysis of ODEs and SDEs. Okay. Which luckily I do have some experience with. So this should be helpful. And also deep neural networks. And in particular, it says flow matching and denoising diffusion models are a family of techniques that allows us to construct, train, and simulate such ODEs, SDEs at large scale with deep neural networks. Okay. So this is the part that I'm not so familiar with, right? So for example, I know how to solve an ODE using the Runge-Kutta method, the classic numerical analysis, but I don't know how they relate to deep neural networks. Okay, so we'll put a question mark here to see how. So Eagle says you need several layers of AI agents talking to each other with proper supervision and planning, of course, to achieve best results. AI plus human isn't enough. It's human plus AI agent and another AI agent. Interesting. I didn't know about that. So thank you, Eagle, for your input. All right, so remark 1, additional resources. While these lecture notes are self-contained, there are 2 additional resources we encourage you to use. Lecture recording, yes, we've just seen that, and also labs. Right, so these are Python worksheets. Okay, okay, I guess at some point we'll have to get our hands dirty and code. Okay, at some point, if we do decide to continue following through the entire course. Okay, so we'll see about that. Sagenator says it doesn't quite seem numerical analysis, like more kind of a programming argument, but they're minimal in place of more math ones. Okay, we'll see about that. Okay, here we have the course structure, which just seems like the same as the list of content. Okay, so you have generated modeling as sampling. We formulate what it means to generate an image, video, protein, etc. Okay, that's cool. That's cool. So this has perhaps this has something to do with Monte Carlo simulation, perhaps. Yes, you have to code eventually. It's like learning how to use Excel. Yeah. Thank you very much. But for this particular session, we'll try to just follow the math. Okay. Next up, we have flow and diffusion models. We explain the machinery of generation. Like, of course, if you're serious about AI, of course, I understand you need to code. But at this point, I'm more interested in the main idea. And it's just, of course, individual approaches vary. But my preferred way of study, it doesn't have to be for everybody, okay? My preferred way of study is to have an algorithm already living in my mind before me touching its digital incarnation. Okay, so that's just my preferred way of studying. Okay, I'm not, of course, not against coding by any means. I'm not crazy. Okay, we explain the machinery of generation. As you can guess by the name of this class, this machinery consists of simulating ordinary and stochastic differential equations. So I guess perhaps you need some background in ODEs, like system of ODEs. So yeah, it seems like I have to, I don't have to, but I would like to do a bridge course on the bare minimum of ODEs, system of ODEs, because there's already so many different topics that we do on the channel that is based on the knowledge of ODEs, PDEs, SDEs, optimal control. It's like the gateway to applied mathematics, really. Okay, we provide an introduction to differential equations and explain how to use them to construct generative models. Next up, you have flow matching, score matching. So we study score functions. So if you have done some statistical inference, in particular maximum likelihood estimation, you likely have seen the terminology called score functions. And that's the gradient. That's the gradient of log likelihood functions. So I hope they're talking about the same thing. Okay. And it says it unlocks SDE sampling and guidance. And what is the guidance? Guidance, we learn how to condition our samples on a prompt. For example, an image of a cat, and how we can enforce adherence to such prompt via classifier-free guidance. Okay, so these are jargons I don't yet quite understand. Latent space and neural network architects. Optional, discrete diffusion models. Okay, interesting. Okay, so required background. This is the official required background. Due to the technical nature of the subject, we recommend some base level of mathematical maturity, in particular some familiarity with probability theory. But I don't think you would need measure theoretic probability theory. Okay, you only need probability theory at an elementary level. That is to say, what continuous and discrete distributions are. You know how to calculate mean and variances. You know what a PDF is, what a CDF is, that sort of stuff. Okay, and some common distribution. I think that should be enough. Okay, I don't think I've encountered through a brief glance that measure theoretic probability is needed. Okay, but if it does, if we do encounter such notions, like from measure theoretic probability, we'll do a crash course on those on a need-to-know basis. For this reason, we included a brief reminder section on probability theory in section A. So that's a appendix. Don't worry if some of the concepts there are unfamiliar to you. Okay, so these are just the logistics, the course logistics. All right. So I think this is the actual first lesson or first actual session of what we're doing. Okay. So we will define mathematically what images and videos are, and perhaps also molecular structure, because it mentioned protein before. All right. So What do they mean mathematically? What is the image mathematically? Let's begin by thinking about various data types or data modalities that we might encounter and how we will go about representing them numerically. Okay, it makes sense. So consider images with h times w pixels, where h describes the height and the width of the image. Oh, that's my cat. Oh. Each with three color channels, RGB, because these are color codes. Right? Does everyone know about RGB scale? For example, if you go here, you can create a new color. How do we do that? For example, if I go to view, you can change the page color. I changed the page color to this, I don't even know how to call this color. It says orange here, apparently, but it doesn't look terribly orange to me. But yeah, color code, you see RGB, is a numerical scale that you can specify the degree of redness, so to say, from 0 to 255, and it's the same for green and blue. Okay, so that's like mathematically, that's a cube in R3. That's an RGB. Yeah, here RGB is a vector that lives in a cube. So yeah, let me just put that down. So this is how computer represent color, RGB. RGB is a vector, let's call it X, that lives in the space 0 to 255. Okay, so I mean in the software, for example, in OneNote you can only put integer value, but just for the sake of mathematical convenience, let's consider continuous scale. Okay, 0 to 255 cubed. Okay, so that's a vector that lives in a 3D space. It lives in a cube. So that's the RGB code. So the image is a data structure. Okay, so you can imagine it is a big grid, and we can specify how many rows and columns in that grid. Let's just do that real quick. Okay, so there, if the height is h, let's just say there are h rows. Okay, and the width is w, so there are w columns. All right, so that's and that's all the pixels, right? That's all the pixels, and in each pixel you have to assign an RGB code. So based on what we just read, for every pixel and every color channel, we are given an intensity value in R. Yeah, so RGB are the three color channels that we just saw. Right, so an image is an element Z in R, H times W times 3. So it's not quite a matrix, because it's like a three-dimensional array of numbers. And that's like a three-dimensional array of numbers. So you can think of it as basically a tensor, right? In a computer science definition. Okay, in a computer science definition, a vector, that is a one-dimensional array, a matrix, which is a two-dimensional array, and higher dimensional array like these ones are tensors. They're a little bit different from the mathematical definition of tensors, which is more restrictive, or the physicist's definition of tensors. So, so this is what we mean. Okay, so for each pixel, you're going to assign an RGB code. Assign RGB code. So therefore, an image is an object that lives in the space R H times W times 3. Right? So that's this object. It's a multi-dimensional array. It's a 3-dimensional array. Right? It needs 3 indices. Right? For example, let's look at one of its elements of this object. Say Z, say 10, 100, and 2. What does this mean? What does this mean? This means at location 10, 100 in the image. That's basically 10 and 100 specify the coordinate in the image. And 2 is the degree of greenness, if you can call it that way, because that's the second color coordinate. Right. So again, let's just say here, that's the intensity value. That's the intensity value of green, for green, at for pixels 10, 100. Right. This is the intensity for green of 10 hundredths pixel. Okay, so the image lives in this space. This is the definition. The image lives in this space. And here actually it doesn't seem like we're imposing specific range for the color channels. Okay, in the software, OneNote, the max value for the color channel is 255, but it seems like we aren't even bothering with that, right? It's just a regular R3. You can imagine, okay, you can imagine there's a tiny little 3D coordinate system sitting in each pixel. Right? So that's basically the mathematical abstraction of an image. Here's the definition. Okay. Next up, video. So video is simply a series of image in time. So now you have a time coordinate as well. So if we have t time points of frames, of course, in actual implementation, you always have discrete time. Right? So even though the image, the video feels like a continuous time object, it's because we're fooled by our eyes, because the frames are played at a rate that human eyes cannot tell. It's jumps, basically. So that's why here we have a 4-dimensional object. That's a video. Okay, so a video is a series of image in time. Okay, so that seems very natural. Okay, so let's put it this way. What's a video? So here a video is an even higher order array. Okay, a higher dimensional array. That's R T times H times W times 3. That's a 4-dimensional array. Okay, and here, for example, let's just say, if let's say Z, say 20, and we're not specifying the rest of the 3 indices. Let's just put it this way. Okay, I don't specify. I'm not specifying these 3 indices. This is just this is represent a frame. A frame, the 20th frame. Okay, this is basically the 20th frame. The 20th frame. That's a video. And big T is the number of frames. So that's a higher order tensor. All right. Okay. So what's a protein? Okay. What's a molecular structure? A naive way to represent molecular structure would be to represent the structure of a molecule by a matrix. Why is it a naive way, though? Interesting. And what does this matrix represent? Z equals Z1 all the way to Z big N. Okay, so it has 3 rows apparently, right? So here it has 3 rows. Let's try to visualize it. So here it has 3 rows and n columns like this. Okay, so there are n columns and there's 3 rows. So where n is the number of atoms in the molecule, and each Zi describes the location. So you can imagine this is some kind of a collection of particles, right? That's a collection of particles, and this is a molecule. The collection of it is a molecule, and you're just going to specify the coordinate of each atom here in a table format. Okay, of course, there are other more sophisticated ways of representing such a molecule. So this is basically a system of particles in classical mechanics, right? But of course, this is a very primitive model because we don't even know how the molecules are connected, right? If you're taking chemistry, you know it's possible to have different configuration for the exact same set of atoms, and you get different molecules. There's no relation, right? You just know these coordinates. I don't know, like for example, should the bond be like this or like this? We don't know. So that's a matrix, but to incorporate such information, what we should do to incorporate such information? Well, I think you can probably represent connectivity as a graph, right? As a graph. And a graph can be represented by another matrix. So a molecule would be 2 matrices in that regard. So let's say this is a connectivity graph, which can be represented by a matrix. For example, this is 1, 2, 3, 4, 5, 6. Right? You get a 6 by 6 matrix. There's a bond between 1 and 3. So you put a 1 here, and everywhere else is 0, right? Because 3 is the only one that 1 is connected to. And 2 is connected to, it looks like 3, 4, 5, 6. It's 3, 4, 5, 6, so you put a 1 in all these entries, and the rest are zeros. And you do the same for the rest. It should be a symmetric matrix because connectivity goes both ways. This is not a directed graph, okay? This is just a connectivity graph. A connectivity matrix, undirected for an undirected graph. And you can, I'm not going to write the rest, you know the idea. So basically, if you want this sort of graphical representation for a molecule, you can pair the coordinate matrix with a connectivity matrix. But this can be done, right? So, of course, there are more sophisticated ways of representing such a molecule. I think the most natural, the most immediate next step would be including connectivity information. But anyway, they're all higher order dimensional arrays, right? Just like a matrix, but just with more indices. In all of these above examples, the object we want to generate can be mathematically represented as a vector, or potentially after flattening. Okay, potentially after flattening. Therefore, throughout this document, we will have key idea 1. Objects as vectors. So I see. So here, by flattening, you're applying a vectorization procedure to a higher dimensional array. For example, let's say the simplest example would be how to read a matrix as a vector, right? So for example, you can force a matrix to be a vector by reading the entries row-wise. So let's say you have a matrix, say 1, 2, 3, 4. Right? A vectorization could be, okay, it could be, say, a row vector that's 1, 2, 3, 4 like this, and you need to put some kind of put some kind of a, I don't know, like a block structure. You can do block matrices, right, to indicate that, well, the first row ends with a 2, right? So yeah, yes. So Christian, thank you very much for answering viewer question. I should probably answer some of myself. Hi Leo, thank you for joining the stream. I didn't know you were here. So yeah, yeah. So guys, Leo lectures in chat. JC Practice Math and Dawn are going to have a review-thon for what we call a SOME, SOME 5, which means Summer of Mathematical Expedition. So basically, they're going to reacting and providing feedbacks to some YouTube videos, some math YouTube videos, and share their thoughts. It's going to be a great fun. Unfortunately, I can't join. I mean, I originally agreed to join, but this week has been really exhausting for me. And this stream on diffusion model was something I scheduled a long time ago. So I wanted to no longer delay this one. So after this, I'll be just pretty much going to sleep, okay, for a very long time. So unfortunately, I cannot do the video reviews tomorrow. So, but by all means, I will post the links for their streams in my community tab, and also Discord server. So go check them out. Anyway, so here, yeah, there's a bond between 1 and 3, but is there a bond between you and me? Yeah, I do believe. Yeah, we had a stream together. There's a bond between us. Would you cover continuous normalizing flow? Actually, I don't even know what that means. And Christian is entirely correct in pointing out that I don't know enough about the subject yet to know. This is very much a study stream. Yes, Dawn factorial. Yes, Dawn factorial. So anyway, thank you very much for providing, these new terms to me, because I don't even know what is a continuous normalizing flow. Perhaps this is something that is covered in the course note, hopefully. All right, so here, these are just some basic examples of quote-unquote data modulation, data modalities. Okay, data modalities. So you can vectorize higher dimensional arrays, okay, and into just one-dimensional arrays, provide you know, well, where the line is broken, right? So you can always do this. So from now on, just to simplify the mathematics, because dealing with vectors is relatively easier, say, than tensors, right? So we're going to treat objects as vectors in RD, where D can be extremely large, as you can probably imagine, right? For example, here, in an image alone, you need numbers of pixels. And in videos, there's also a time dimension. So T times H times W can be ginormous. Right, so we're going to represent our data as a vector, and typically speaking, very high dimensional vectors. All right. So I wonder if we will veer into the subject of high dimensional probability as well, because that's an insanely popular topic in mathematics right now. High dimensional probability and some highly non-intuitive results can be said about high dimensional probabilities. All right, so that's the key idea here. Data as vectors. Z belongs to RD. Okay, this is tensors vectorized. Okay, so next up here, a notable exception above is text data. Why is text data different? Which is typically modeled as a discrete object. Right. Here, see R to the D? R is a continuum, right? So text data is modeled as a discrete object by language model. While continuous data, Z and RD is our main focus, we will also study text generation in section 7. Okay, that's basically chapter 7. That's the optional part of the course. All right, so we know what we mean by data, right? We know what we mean by image, a video, and even molecular structure. But what do we mean by generation? Right? What do you mean by generating data, right? Generation here means sampling. Okay, so this sounds awfully similar to Monte Carlo simulation, which is essentially generating random numbers based on some postulated distribution. Right, let's see if that's what it's about. All right, let us define what it means to generate something. For example, let's say we want to generate an image of a dog. Naturally, there are many possible images of dogs that we would be happy with. In particular, there's no single best image of a dog. Rather, there's a spectrum of images that fit better or worse. Okay. In machine learning, it is common to realize this diversity of possible images as a probability distribution over the space of images. Remember, a space of image is just a Euclidean space, RD. Well, we don't really know is a Euclidean space because we have not specified what sort of distance function that we impose on RD. But basically here you have just a d-dimensional space of tuples, right? D tuples. And you want to define a probability distribution over that space to represent possible images, right? Of course, this is a very broad concept, okay? Because, for example, let's say this is just a simple Gaussian distribution. What do we mean by saying the mean of the Gaussian distribution mu is 10? What do we even want by specifying the parameters of this distribution? Does that mean preferability? What sort of images are we looking for, right? Say, are you specifying a particular breed of dog? Do you want to generate an image of a Chihuahua? Is that what you want? Or something else? And perhaps that has to do with the parameters of the distribution, but we shall see. Okay. Next up, in machine learning, we've already read that. We call such a distribution a data distribution and denote it as P data. Okay. So we have a distribution over the space of quote-unquote objects. Okay, and mathematically we can think of P data as a probability density, i.e. a function P data. This seems like a probability density function. This seems like a probability density function in just ordinary probability, like a Gaussian density. Right? It's the function that maps from RD to R greater or equal to 0, that assigns each possible object a likelihood. So this is pretty much probability density because likelihood can numerically equal to the discrete probability function, which is a probability mass function, or the probability density function, which is we're talking about here. So basically this is P data is just the usual density in your introduction to probability class. Of course, it's much more complicated because of the high dimensional nature of the object, right? So that's a data distribution and a probability density that parameterize the data distribution. All right, so in the example of dog images, the distribution would therefore give higher likelihood to images Z that look more like a dog. What do we mean by look more like a dog? This is something that needs to be formalized. Therefore, how good an image or video / molecule fits around the subjective statement is replaced by how likely it is under the data distribution. How likely it is under the data distribution. Interesting. So it seems like we're looking for the mode of the density then, right? You want likelier values, right? You want likelier values. So there's a nice analogy with maximum likelihood, method of maximum likelihood estimation in statistical inference, seems like. All right. So yeah, with this we can mathematically express the task of generation as sampling from an unknown distribution. Interesting. How do we even sample from an unknown distribution then? Because Monte Carlo simulation refers to sampling from a known distribution. Let's say if you know, if you're talking about, the standard normal distribution, normal 0, 1, we know how to sample it. Right? There's a method. I mean, the detail doesn't matter, but basically you need to specify the distribution before doing Monte Carlo simulation because, well, it's just how things work. But here we need to sample somehow from an unknown distribution. So that's something we need to pay attention to. Okay, but for now, let's just write some notes here. So what is sampling? Sampling is here. Sampling is all right, so here, generating an object is modeled as sampling from a data distribution. All right, so this is a classic notation of a random variable following a distribution. So here, this is another key idea. Right, so this is key idea 1, key idea 2. This is very high level stuff, all right, but it's still very useful. Because once you have the mathematical abstraction, then you're ready or more likely to apply existing knowledge. Right? For example, you can apply linear algebra to key idea 1, data as vectors, and you can apply knowledge of ordinary probability theory, mean variance, densities, and whatnot to idea 2. Okay, so what do we mean by generation? Generation is sampling. Generation as sampling. So here we have, first of all, a data space earlier, and the data distribution, quote unquote, data distribution is a probability distribution over the data space. Data space RD, which we just defined. So data is vectors. And now the data distribution is described by the probability density function. All right, so the probability density function is denoted as p data. P data. So sampling just means sampling. It means meaning select z according to the probability law p data. According to p data. Okay, but p data is unknown, and this actually what puzzles me the most. How do you even sample from an unknown distribution? Apparently this is unknown. So you need to pay attention to that. All right, so next up, a generative model is a machine learning model that allows us to generate samples from P data. Okay, fair enough. In machine learning, we require data to train models. Interesting. So does that mean you're going to approximate P data with some empirical distribution? All right, let's keep reading. In the generative modeling, we usually assume access to a finite numbers of examples, sampled independently from P data, which together serve as a proxy for the true distribution. So basically, that's the empirical distribution. So what it now means is more clear, because P data is a theoretical distribution that you have no exact knowledge of. And what you're going to do is to approximate the true distribution P data by an empirical distribution. So that's basically your learning material, the finite number of examples. Okay, so that's the data set. And I guess we're likely to assume that the data set is IID, like in classical statistics. Right? So that's a data set. That's a data set. So, it's like, sorry, here, in elementary probability, we know a Gaussian curve is a infinitely smooth bell curve, right? But let's say if you don't know the formula of the Gaussian density and you want to approximate it, you can collect a bunch of data from this Gaussian distribution, and you can create a, say, like a histogram, a bunch of rectangles. And that will be an empirical distribution. And you can use fancier tools, such as kernel estimation. The histogram is a particular example of a kernel density estimation method. So the point is you can approximate the true distribution by using a finite number of samples. The exact mechanism is unspecified at this point, but this is a very high-level idea. Okay, the data set is supposed to serve as a proxy for the true distribution. So that's very classical statistics. Right? So we can do that. Okay, let's put it that way. So is that a next idea? Okay, next idea, key idea 3. The idea is 3. Let me just put it this way. So P data is unknown, so therefore it must be approximated. Is approximated by empirical distribution, by an empirical distribution. Empirical distribution is formed, which in turn is formed by a data set. Data set itself is a random sample. Formed by a data set, a random sample. From the probability distribution. So a random sample Z1 all the way to Z big N. A finite list of realizations from P data. So that's the key idea 3 here. Okay, so basically, if we let's say think about, say, images, right? Dog images. You're just gonna take a bunch of dog images, and remember, what's a dog image? What's a dog image? A dog image is a vector here. The dog image is now just a vector, and you can mathematically represent a vectorial distribution as a function from RD to R. RD to R. So you have a large number of dog pictures, which are then represented by vectors, right? And you can represent it by vectors. So a vector in RD, right? You can count the relative frequency of a specific value in the first coordinate. right? Because that's basically what empirical distribution is about. Like a histogram is counting empirical frequency. So that's how a proxy distribution or empirical distribution can be constructed. So yeah. All right, so let's, I'll read some chat because I haven't been following chat. Okay, I was just trying to understand the key ideas here. So it's not so much looking for the mode as a sampling from the distribution. Okay, okay, because I don't know what I was talking about, right? So I mean, if let's say you want to maximize likelihood, is the results the mode of the empirical distribution? Okay, it doesn't have to. Okay, I don't think it have to. I don't think it will have to. But anyway, we'll look for specific methods later because this is, I mean, we're not even at that stage yet, right? So this is just the ideas, right? The key ideas here. All right, it's kind of back where the model / simulation is what defines the distribution. Is what I think the model is P data, right? This is some postulated true distribution that exists for, say, all the dog images, right? We don't know the exact details of it, but through finite samples, through real world samples, right? So actual dog images, through actual dog images, you are able to approximate the distribution of dog image, right? The true P data. And simulation would be drawing random samples from that distribution, from that proxy distribution. So that's basically, so first you have the statistical inference problem. Okay, so let me just put it that way. So here in, where should I put this? So here you have data, and which is, say, actually, you know what, never mind. I want to kind of represent what we just discussed in the flow chart. You have data set, right? And you have data distribution. And finally, you have the output, which is the result of generative AI. The data distribution, and finally you have output. All right, so here, from data distribution to output, that would be as generation, right? Quote unquote sampling. That's key idea 2, generation as sampling. Generation as sampling. So basically it boils down to a Monte Carlo simulation, MC simulation. Which essentially is the same as flipping a coin, right? That's the same idea, right? So that's this step, because but in general the data distribution is unknown, therefore you need to approximate, right, from the data set to approximate data distribution. So this is I guess the learning, you can call this the learning procedure, right? In statistics we call this inference. In computer science we call it machine learning. You're learning the data distribution, or inference, right? And here you would do some kind of fitting method, right? So you're doing parameter optimization, like maximum likelihood, or perhaps you can use a non-parametric method, such as kernel density estimation. So this is an estimation problem. That's what I'm trying to say. So use data set to estimate the data distribution, and then you generate output using some sort of Monte Carlo simulations. It's a very high-level description of the overall flow chart, right? So that's the procedure here, how these ideas connect. Okay, so I think I have some background in both estimation and MC simulation, but I never applied it to this particular setting. Okay, so let's see if there's anything new new techniques. Well, I mean, probably there will be that we need to pick up. All right. But overall, that's the structure. Okay. For images, we might construct a data set by compiling publicly available images from the internet. There might be copyright issues in that process, but let's just leave the ethical subject aside. But it does exist. For videos, we might similarly look to use YouTube. Okay. For protein structures, sources like RCSB, Protein Data Bank, provide hundreds of thousands of experimentally resolved structures. As the size of our data set grows very large, it becomes an increasingly better representation of the underlying distribution. Well, of course, that's how statistics works, right? The law of large numbers. Provided under ideal circumstances, the larger the sample, the better the approximation, roughly speaking. All right. Okay. So this doesn't seem like very hard to understand, but let's keep going. Then we have say guided/conditional generation. Guided/conditional generation, because earlier here we don't have any user input, right? We don't have any user input. This entire process we just described earlier, this is unguided. This is just purely based on observation. It looks at the data set and it creates the approximation of the data distribution, and it uses that approximate distribution to generate output. Right? There's no user's preference or whatever being involved in the process, because this is unguided, quote unquote, unguided generation. Okay, and now you have guided conditional generation, right? So perhaps vibe coding. Have you guys heard of vibe coding? Vibe coding is one such example. Right. Just want to make sure everyone is on the same page. What is vibe coding? Vibe coding is a software development approach where you build applications entirely through natural language prompt rather than writing code manually. Right. So you describe what you want. The AI generates host and the working software. You test it and you provide feedback until it works the way you want. That seems to be guided generation. Right. In many cases, we want to generate an object conditioned on some data Y. For example, we might want to generate an image conditioned, okay, on this prompt right here. A dog running down a hill covered with snow with mountains in the background. That's a prompt. We can rephrase this as sampling from a conditional distribution, because the unconditioned distribution is just a dog, right? It doesn't care about what the dog is doing, what background it is. Right? Here we're saying something specific. And rephrase is sampling from a conditional distribution. So guided generation is sampling from a conditional distribution. P data, and here we'll talk about conditional distribution a little bit if the main text calls for it, but there is a background here, I believe, on the reminder and probability theory that talks about how conditional distribution is defined and whatnot. Okay, so basically, I hope everyone, I mean not everyone, because now it's we have 15 viewers in chat right now. Okay, yeah, perhaps we can talk a little bit about how conditional distribution is defined when we see a specific example. But basically, you can think of a conditional distribution as the P data, but with some extra information. P data with some extra information. Okay, it's still a distribution over the data space. Okay, but the samples are smaller, right? So not the samples, sorry, not the samples, but the allowable outcomes that counts into this distribution is a smaller set, because you're, say, for example, you're only considering dogs running downhill, covered with snow, with mountain in the background, right? So that's conditional distribution. That's called a guided data distribution. We call p data dot slash y dot given y the guided data distribution. So the guided generative modeling task typically involves learning to condition on an arbitrary rather than fixed choice of y. What's interesting is what this y should live in, right? What this y should live in. That's a much more difficult question to answer. Y is a conditioning variable, but right now it's unclear what this means. We know what a data is. Well, a data is just a vector in RD. How would you represent y though? So how do you encode this sentence here? It says y equals this sentence. Is that like, how do you, I mean, I guess you have to, do you actually encode the list of strings or something else, or some information based on it? Because I don't know, like I have no experience with natural language stuff, all right? So basically, I think at some point we'll have to formalize the space of conditional variable as well, right? But basically at this point we can just consider y being some extra information that allows you to change the probability measure over the data space, right? So let's continue. So that's we call a guided data distribution. The guided generative modeling task typically involves learning to condition on an arbitrary rather than fixed choice of y. Using our previous example, we might alternatively want to condition on a different text prompt, such as y equals a photorealistic image of a cat blowing out birthday candles. Right. So in that case, the data space is the same. The data space is the same. It's still just a vector in RD, because RD doesn't know it's a dog or a cat. It doesn't care. It's just a bunch of pixel values, right? So if you're using a different prompt, now you want a cat blowing out birthday candles, which seems to be rather popular on YouTube. I mean, not specifically blowing up birthday candles, but there's a lot of AI slops on YouTube of AI cat videos. Have you guys encountered such things? I've encountered a lot because I'm a cat lover, so I watched a lot of cat videos, and YouTube have been recommending me a bunch of AI cat videos, which I'm actually guilty of watching. So here we have a question in chat. Does the dot just means unconditional variable? So for example, it just means that it's the argument, okay? It's the argument of the function. So p data, let's say if p data is a normal distribution, say p data equals, say, a normal mu sigma squared. That means the function p data of z equals 1 over the square root of 2 pi sigma squared times e to the minus x minus mu, or z minus mu quantity squared over 2 sigma squared. All right, so that's p data of z. And of course, if you change the variable name, it's the same function, right? Let's say if you change that to t, that doesn't change the function. It's still the same bell curve, right? So in practice, we often write just p data dot to represent the same function, but the variable name doesn't really matter. So that's the meaning of dot. Okay, that's the meaning of dot. So it's just here you can put the dot as z. It doesn't matter. Okay, it's the variable that you want to generate. Sorry, it is the variable that represents the data that you want to generate. Okay, so remember, p data here is a distribution of RD. P distribution is a vector in RD. Here, you can substitute dot by any arbitrary vector in RD. You can substitute the RD value here, and it will return a probability density value. Okay. It's like in linear algebra, we often write inner product, say angle bracket dot, comma, angle bracket, dot angle bracket, right? That's an inner product. It just means that these are placeholders for two vectors, for two vector arguments, right? This is the same. The function is ready to receive a vector argument and will return a non-negative real value, because that's the probability density, once received an actual data value. So this is just a notation for a placeholder of argument. Now, no worries. All right, so here, let's see, what's the, where were we? Right. We therefore seek a single model which may be conditioned on any such choice of y, the conditioning variable. It turns out that techniques for unconditional generation are readily generalized to conditional case. Okay, interesting. So mathematically speaking, the focus would be on unconditional generation, which is the workflow here. Because essentially, you're just changing p data to a different distribution. But perhaps also you gotta worry about, say, the intricacies of defining conditional distributions later. We'll see about that. Therefore, for the first three sections, we're focused almost exclusively on the unconditional case, but keeping in mind that conditional generation is what we are building towards. Okay, cool. So let's put that down. Here we have key idea number 4. So guided, quote-unquote, conditional, right? That's the name? Guided slash conditional generation, yes. Guided slash conditional. Generation is, you want to, here, means select z according to p data. There's a conditional distribution p data given y, where y is a conditioning variable. And at some point we'll have to worry about the distribution of y, probably. Conditioning variable. All right. Okay, cool. So if you have some experience with statistical inference and perhaps Monte Carlo simulation, this should not seem too radical to you. All right. So hopefully we can keep things that way. Hi, Chloe. Thank you very much for joining the stream. Yeah, I remember you from my stream on the physics of stochastic process, or stochastic process for physicists. So thank you very much for returning. All right, so let's take a look at the summary here. So okay, so this is a very high level description. All right, so we'll see if our understanding matches the summary here. All right, so abstractly speaking, a generative model is an algorithm that returns sample from z followed from p data, or at least approximately. If p data is a distribution of the images of dogs, this algorithm would return random images of dogs. In this course, we will focus on the specific constructions of generative models using flow or diffusion models, as these represent the current state of the art. However, it is important to keep in mind that many other generative models were developed, and maybe even more that will be discovered in the future. Well, that's almost guaranteed. Summary 2. Generation as sampling. Remember, we did have one key idea, generation as sampling. So this is a summary so far. In this work, we mainly consider the task of generating objects that represent as vectors, Z and RD, such as images, videos, and molecular structures. Generation is a task of generating samples from a probability distribution, P data, having access to a data set of samples Z1 all the way to Zn, following the distribution P data during training. Right, so this is the training part. Right, this is the training part. So the training part is all about the estimation of the distribution P data. Right? And because of P data is a distribution over a very high dimensional space, typically speaking, there's got to be some special consideration based on that too. Because the probability distributions in high dimensions behave very differently. Perhaps the so-called curse of dimensionality will play a role here. Okay, we'll see if that's actually needed. So guided generation assumes that we condition on the distribution on a label y, and we want to sample from the conditional distribution, having access to data points. Okay, so here you see the data points, they all have the same conditioning variables. Okay, so basically in our, say, the dog example, you would have a bunch of images of dog running down a hill covered with snow which mounted in the background. So all of these images needs to have the same value for the condition variable. Okay, so of course this is a highly specific prompt. Well, as most prompts are. This is a highly specific prompt. Do we actually need a large number of images for every prompt? That doesn't seem very realistic, right? Right? Of course, we know that training a model requires monumental amount of data, but still, I don't think it would be feasible if you're going to collect a large sample of data points or a large sample of images, say, for all these complex prompts. How do we overcome that difficulty? Right? Perhaps this will be addressed as well. All right. So each condition has its own distribution. Yes, theoretically. Because we can just write down the distribution here. So P data of Z given Y, right? If you know some basic probability theory, this would be the joint distribution. That would be P of Z and Y over P of Y. So that's the definition of conditional density. So P of Y is the marginal distribution of Y, which is why I was talking about at some point I guess I'll have to worry about the formalization of Y, because this is just a text. Are we actually going to encode this text in some way, or are we just going to like select the main idea of a sentence? Because I never done any natural language stuff, so I don't know how what would a P of Y look like. Okay, but that's basically the idea here. Okay, so you can think of the usual Venn diagram situation. This is Z, this is Y. Okay, you're looking at the joint distribution. This is PZ of Y, that's the intersection here, divided by P of Y. So essentially your sample size shrinks. Right? This is a big omega. Your sample size is now just Y, and you're calculating the portion of the intersection relative to P of Y. So that's what I mean. This is theoretically how would you define a conditional distribution, but right now I have no idea how would even P of y be defined. We don't have a formalization for that yet. Okay, but in practice, the y's in the training set will be different. Yeah, right. That's here. I mean, theoretically, right, you should fix y because that's, well, literally the meaning of conditioning. But how do you actually accomplish that in a feasible manner as an engineering project? We'll have to see about that. Right. That's just the philosophy of what we're doing. Our goal is to construct a generated model, i.e. a model that returns samples from P data after training. Okay, all right. So I think we're good with that. And now let's take a look at the tools, the main tool that we will be developing. All right, the flows and diffusion models. Okay, what's a flow? What's diffusion? Right. What are these buzzwords? In the previous section, we formalized the generated model as sampling from a data distribution P data. Further, we formalized our goal. To construct a generated model, an algorithm returns a sample, Z follows P data. In this section, we describe how a generated model can be built as a simulation of a suitably constructed differential equation. Wow. That's pretty amazing, isn't it? Because I don't know, I have no idea how on earth differential equations are connected to Monte Carlo simulations. I don't know about that. Okay, so let's find out. For example, flow matching and diffusion models involve simulating ODEs and PDEs, ordinary differential equations and stochastic differential equations, respectively. So flow matching simulates ODEs and diffusion model simulates SDEs. Okay, so let's put that down. Here, this is the next section, right? Here, this is section 2. Hang on. Yeah, so that's actually section 2. You know what? I'll start a new node. Diffusion models, this is intro. Because I want to keep things separate. Here, this is, let me change the page color real quick. So this is August 28, diffusion model. And what's the section name? Flow and diffusion models. All right, so here our goal is still, at this point in this section, I don't think we're talking about learning the distribution, right? Here is just the generation part. Assume for the moment that P data is known. How can you return a sample from it? Right? So that's the idea here. And here, our goal is to generate Z follows from P data. Okay, and what we're doing is this. So first of all, you have flow models. Okay, so flow models simulate okay, so you have flow models. Flow models simulates ODEs. It's a deterministic dynamical system. And diffusion models simulate SDEs. Right? In the last couple of streams, we've been talking about the physics of diffusion. Right? That was the first episode, first and second episode of the Stochastic Process for Physicists series. So the term diffusion came from the study of Brownian motion. And in particular, there are two main approaches to the study of diffusion, the Brownian motion. The Einstein's approach, which models the distribution law for the stochastic process. Right? So Einstein derived the diffusion equation based on probabilistic assumption, whereas Langevin modeled the trajectory of diffusion, the trajectory of the random walk directly, using an ODE with a noise term, which is nowadays known as the Langevin equation in physics and SDEs elsewhere. Okay, stochastic differential equation. So we're going to simulate ODEs and SDEs and somehow connect that to generating data point from some distribution. Okay, so this is our goal, and this is the method. The method that we're going to cover. All right, so let's go. Here, the goal of this section is therefore to define and construct these generative models as they will be used throughout the remainder of the notes. Specifically, we first define ODEs and SDEs and discuss their simulation. Second, we describe how to parameterize an ODE/SDE using a deep neural network. Wow, that's crazy. Okay, so this is not traditional numerical analysis, isn't it? Because I have no idea how would you parameterize an ODE using a DNN. Okay, what's first? What's first? This is second, right? What's first? Okay, we'll first define ODE and SDEs, okay? Which I think this is relatively familiar with, or at least hopefully the audience already has a working knowledge of ODEs, or at least intuitively how they work. And we just did a session on SDEs. Not their simulation so far, but it's crazy how many fields are connected. I know, right? I know, right? This is, this is the beauty of math. This is the beauty of one of the beauty of math. One of the aspects of beauty of math is that seemingly unrelated things. I mean, I'm still amazed every day because I would consider myself to be relatively well versed in ODEs and SDEs, yet I still have no idea how they're connected to a deep neural network. Yeah, that's why math can be addictive. Exactly. There's always one more connection to unravel. It's crazy, really. Yeah, I absolutely agree. It's one of the greatest joy of learning mathematics. Is just how seemingly disconnected phenomenon have shockingly similar foundations. Like, yeah, anyway, so let's put that down, all right? So what do we want to do? We will cover basics of ODE and SDEs. Basics of ODEs and SDEs, and what else? And parameterize, quote unquote, right? I don't know what that means yet, right? Parameterize ODEs / SDEs using deep neural net. So this is such a, as you can see, this is such a interdisciplinary field, diffusion model and flow models. And it pushes the boundaries of what is usually segregated in different academic silos. Neural networks, right? For example, ODEs are studied heavily by applied mathematicians, physicists, and engineers. SDEs are studied by financial mathematicians and also control engineers. And deep neural networks are studied by, well, computer scientists. But traditionally speaking, not an awful lot of people are well versed in all of these areas. Right? it forces researchers to learn about other fields, which is one of the principal roles of applied mathematics. Applied mathematics is not so much about proving new theorems, but it's absolutely crucial. It's the glue of all science, is what I want to consider. Applied mathematics is the glue of all science. Because without applied mathematics doing the ambassador role between different disciplines, I don't know how these kind of fusions between disciplines can happen at all. Right. So applied mathematics, contrary to popular belief, is really the flagship of the entire scientific enterprise, if I can call it that way. All right. Anyway, so let's continue. Here we have the just learned that you can derive Maxwell's equation from Navier-Stokes. You sure about that? I have no idea. Okay. Okay. Anyway, let's try not to digress too far, but let's start with some actual math. Okay. So earlier we just did the formulation part of the problem, and now we're actually dealing with actual mathematical tool. So we start by defining ODEs. An ODE, a solution to an ODE, is defined by a trajectory. Okay, perhaps we should say something about the definition of ODE. Okay, it feels a little bit of jumpy, right? Overall, the flow of the course notes has been excellent, but perhaps here they're assuming sort of backgrounds in ODE. But basically, I'll do some extra writing here to fill in the gap here. Okay, a solution to an ODE is defined by a trajectory, a function of the form x. Okay, so x is a function from the interval, closed interval 0 to 1 to Rd, and t is mapped to xt, and mapped from time 2 to some location in the space Rd. Every ODE is defined by a vector field. Okay, we'll have to do our own writing. Okay, i.e. a function of the form, a vector field is denoted as u. U is a function from Rd times 0 to 1 to Rd, x and t to ut of x. Okay, for every time t and a location x, we get a vector ut of x in Rd specifying a velocity in space in figure 1. What's figure 1? Okay, this is figure 1. All right. Anyway, we'll come back to that. Because I mean, this is rather incomplete introduction. I will write some notes myself as promised. An ODE imposes a condition on a trajectory. We want a trajectory that follows along the line of a vector field ut, starting at the position at the point x naught. We may formalize such a trajectory as being the solution to the equation d over dt xt equals ut of xt. Why 0 to 1? Yeah, exactly. I don't know why. Perhaps it's just for simplicity. Perhaps it's just for simplicity. I mean, you can always, perhaps in the flow model application, we're almost always interested in the time evolution over a finite interval. Okay, and you can always normalize a finite interval, a finite interval to 0 to 1. You can always do that. You can scale your time to that range, and it simplifies the analysis, the theoretical development, I suppose. All right. So you want a trajectory that follows a line of vector field ut, starting at the point x naught. We may formalize such a trajectory as being the solution to the equation, the ODE, and the initial condition. Okay. So it's time to do some writing. Okay, so I don't assume everyone in chat knows about ODE already. So let's just write the following. Okay, background in ODE, and we'll do an example. Why don't we do the the celebrated simple harmonic, no, perhaps not harmonic, but damped oscillator. Okay, some background on ODE. So we care about ODE of this form. This is the form that we care about. Okay. Not all ODEs can be written this way, but it's a general enough setup for us to work with. So here you have the unknown function xt. We write d over dt of xt equals, which can also be written as simply xt dot. Okay. Xt dot notation is very popular in physics, and this is given by the right hand side, which is ut of x of t. Ut of x of t, that's the vector field. Okay, that's the vector field. So ut, where ut of little x is a given function. So this is an ODE. Okay, this is a here actually this is a system of ODE, to be more specific. Is a given function. Is a given function here. Actually, t is also considered a variable. Okay, so really, what we truly mean is u of t and x. Okay, so here you actually have two arguments. This is a given function. The time variable is assumed to take value in the closed interval 0 to 1. And the second argument, which is a vector, lives in the space Rd. Remember what Rd is in our setup. Rd is the data space. Okay, let's take a look. So here, Rd is data space. The data space is the collection of quote-unquote object. It can be a video, can be a molecular structure, image, whatever you want. Right? I mean, not whatever you want. It does not include text, for example, but continuous objects. A continuous object. So basically, here we're earlier we introduced the notion of a probability distribution over the data space. Oh, that's my cat. She's so cute. Oh, I'm doing important thing here. Okay. Anyway, so here we have a different kind of object defined over on Rd. Right. Earlier we have a probability measure. That's p data. And now we are defining a time-dependent vector field over Rd. Let's draw the picture. So ut of x is a given function that maps from 0 to 1 times Rd to Rd. The important thing is cat petting. Yeah, I know, right? Some things in life is just more important, even than math. Right? So this is what ut of x represent. So let's say this is u1, okay, ut1 of little x. And this is our space, Rd. So it means at time instance t1, every point in the space Rd is given a vector. So that's the output here. So it's like the how do you put it that way? So it's like the wind diagram. is that what it's called in weather forecast? So at each point, say on the map, you know which way the wind is blowing, and you know the strength. Right? So it's very fluid. It's very a fundamental idea in fluid dynamics. It's like the velocity field of the fluid. Okay, so it goes like the vector field goes like this. All right, at each point in the space Rd, okay, you're assigning a vector, a new vector Rd attached to it. So you can think of the vector Rd and the output has a starting point at its location. So here, let's draw a specific point here. This is x. Okay, this point is x, and this vector that is attached to the point x is the vector ut of little x. Right? And in general, this is a time-dependent vector field. So imagine the meteorological condition in the atmosphere is changing. So at this instance T1, the wind is blowing like this at each point. At a second instance, it may change direction and strength. So this is a time-dependent vector field. It's not necessarily a steady one. All right. So let's say the wind totally reverses its direction. That's possible, right? It goes like this now. So that's the second vector field. Right? In general, it's a time-dependent vector field. Let me put it that way. So this is what we call a time-dependent vector field. Right? Here's a quick example from physics. Damped oscillator. I think I gave this example a few times in other sessions because it's such a popular model. It's quite useful as well, not just theoretically but also practically. So this is a damper, and you have a spring attached to it, mass spring system. So the images flow over this vector field u, and the vector field is not fixed and changes over t. But what is t? T is, well, the parameter. Well, we don't know what t is, right? We don't know what the meaning of t is yet. Good question. Yeah, good question. I think perhaps that's the iteration in the training method. Like, you want to. I have no idea. Okay, I don't want to say anything that's unsubstantial. All right, so let's just consider t to be some scalar parameter whose exact meaning is unclear now. So here you have this mass spring system. I just want to give a concrete example of a system of ODE. So by the Newton's second law, you have mx double dot, second order derivative, equals minus kx. That's the spring force, minus cx dot. So assuming that the damping force, okay, damping force is opposite to the direction of the velocity and is proportional to the speed. All right, so that's drag. That's damping. That's a damped oscillator. Damped oscillator. All right. And you can easily represent this second order differential equation into a system of differential equations. So by doing that, we use a standard trick. We write x1, the new variable, define x1 to be x, and we define x2 to be x dot. Okay, this way we get a system, right? A system of ODEs in R2. A system of ODE in R2. First of all, you have, just by the definitions of x1 and x2, you get a differential equation for free, which is x1 dot equals x2. Because x1 dot is x dot and x2 is x dot. So x1 dot is just x2. All right. So next up, you can rewrite the original Newton's second law into this form. So let's just divide by m on both sides, and we get x double dot equals minus k over m. Minus k over m times x minus c over m x dot. All right. So that means x double dot is just, well, it's x2 dot. So x2 dot equals minus k over m times x, which is x1, and then minus c over m times x dot, which is x2. So that's the system, and you can rewrite this into an equivalent matrix form, which is the same as d over dt times the vector x1, x2 times, here we want a matrix multiplied by the vector x1 and x2. So that's a linear system, because you see x1, x2 on the right hand side, they're all linear. The first row should be 0, 1, because it has no x1, and the coefficient for x2 is 1. All right, and the second row should be minus k over m, and then have a minus c over m. All right, so or you can write it as x vector dot equals, say this is the vector A, right? That's the vector, the matrix A. The matrix A times the vector x, where A is the 2 by 2 matrix, 0, 1, minus k over m, minus c over m. Okay, assuming that the parameters k, m, c are all constant, A is a constant matrix. That's the simplest scenario. And you can consider the right-hand side as the vector field. Right? This is the vector field. This is u t of x, although it does not explicitly depend on t. So that's a time invariant or a steady vector field. And plotting the vector field is rather easy. Right? You just select a number of grid points, and at each grid point you calculate the right-hand side, a times x, and it will give you a vector direction. Okay, which I believe should look like, hang on, how should it look like? So if, let's say, I'm just going to select one point here. As an example, all right? So as an example, the vector field A at the point 1, 0 should be what? This is the point 1, 0. The point 1, 0. So let's multiply the matrix 0, 1 minus k over m minus c over m times 1, 0, and this equals 0. Indeed 0, and you have minus c over m. All right, so the vector point downward like this. At the point 0, 1. Okay, so and let's try another point, say a times 0, 1. Will be this point right here. Let's see what the vector direction looks like. Got 0, 1 minus k over m minus c over m, right? These are all, these vectors aren't just mathematical abstraction, they carry physical meaning as well. We'll talk about that in a second. So here you have this is 1, and this is minus c over m. All right. The cats are fighting. Please. Okay. Make my life easier, will you? All right. Okay. Anyway, so here you have the second vector, which goes like this. So, and you can do this for every point that you like. Right, so this is x1 axis, this is x2 axis. So you can draw a great number of arrows like this, starting at the point that you picked, and you calculate the vector, and you draw the vector direction, and this way you get a vector field. And eventually, I think you should get like a spiral. You should get like a spiral like this. Oops, no curved vectors. You get a spiral like this. And as it spirals, there's this tendency towards the origin. Because of physically there is drag here. There's a damping. So for all possible initial conditions, eventually the physical system loses energy. The energy gets dissipated through damping. So it returns to its equilibrium position, where x1 is 0 and x2 is 0. right? So it should. I mean, if let's say if the damping C isn't too strong, there will still be oscillation. Right? That's very intuitive, but it does so in a manner with decaying amplitude. So the continuous trajectory that Christ, what are the cats doing? Let me just give me 1 second. So basically, what happened is a friend of mine left his cat at mine because he's on vacation, and the new one has trouble adjusting to well, my place with the other two cats. So, I mean, so far she seems to be doing mostly well. All right. So basically, I was talking about the flow. Let's say, imagine you do this sort of a vector graphing. Oops. A lot. At many grid points, and eventually you will discover there's a flow pattern to it. And physically, it's not too difficult to imagine that you can have a flow that is spiraling towards the origin due to the loss of energy. Okay, so that's the trajectory here. The solution is a function, which is x vector as a function of t in the space R2. This is what we call a trajectory. Right. So in general, the solution to the ODE is called a trajectory. And typically speaking, we should have an initial condition. For example, in the damped oscillator model, you know the initial position and the initial velocity. That gives you the initial values for x1 and x2. So it's not just an arbitrary trajectory, but a trajectory with a given starting point. Okay. So this is background on ODE. This is a form, and you have the ODE, and you usually also have an initial condition, say x naught equals, say, little x0. Right. So that's the initial value problem. All right. So the solution is called the initial value problem. Okay, IVP. Solution to the initial value problem is called a trajectory. All right, and of course here we gave an example that is time independent. We gave an example of vector field that is time independent. You can easily conjure up some vector field that is time dependent. Say you can add an external driving force to the system, time dependent vector field. Right, so here you can imagine Newton's second law being mx. A trajectory is a vector field? No. A vector field, as we said, is a function from 0 to t times rd to rd. A trajectory is a function xt, which maps from 0 to 1. Okay, 0 to 1, that's the scalar parameter, to rd. It basically tells you, okay, it basically tells you which the exact position in the coordinate rd at a specific time. So a trajectory is tangent to the vector field at every point. At each point of the trajectory, it's also called the integral curve. It's also called the integral curve. So you can imagine the vector field being some kind of a force field, like a gravitational force field. And the trajectories are the force lines. It tells you if you plot the vector field for a sufficiently large number of positions, and you can trace out the direction of the vector field through a continuous curve. Is this how vector field is defined in Calc 4? Pretty much. Yeah, this is pretty much. This is very much an elementary introduction to elementary definition of vector field. In more advanced treatment of vector field, the codomain of a vector field is really the tangent space. It should be T. Okay, it should be the tangent space. The tangent space of RD. But in elementary introduction, we do not distinguish the tangent space of RD and RD. That's too much. All right. Okay. So basically, I was saying that you can easily supplement, augment the model with a time-dependent term. So you can add, say, an arbitrary driving force. So you can add, a driving force f of t. Maybe there's a motor connected to the oscillator or something. You can adjust the input. Right? This is what we call an input in engineering. Control engineering, f of t is called an input or a control function, which is a function that depends on t explicitly. This will be called an open loop control system, because the control does not depend on the state variables. All right, and through the same procedure, you can say define x1 and x2 and whatnot, and you get this system, which is x1 dot x2 dot equals the same matrix A times x, which is 0, 1, minus k over m, minus c over m, times x1, x2. Okay, because perhaps I'm spending too much time on ODE. I really want to get to diffusion today. Hopefully we're good with time management. All right, so here, at least we'll try to give a definition of the diffusion model. Hopefully that's possible. We'll do our best. Okay, we're not going to push things. So this will be 0 here, and minus, just positive, f of t over m. F of t over m. So let's call this vector f. Let's call this vector f. All right. So here you have ax again plus ax plus f of t. So this is a time-dependent vector field. Time-dependent vector field. So time-dependent vector field is much more difficult to visualize, because in a steady state, or not the steady state, but in the time invariant situation, the vector field does not change over time. So you can say that the trajectory is always tangent to the vector field. But here, because the vector field changes over time, right? The trajectory is still a function from 0 to 1 to RD. This is still the case for time-dependent vector field, but it is only tangent to the vector field at a specific time. Right? At specific time t, the trajectory is tangent to the vector field at that exact time. Okay, so it's much more difficult to visualize time-dependent vector field. But the point is here, you know the direction. Right? You know the direction of the trajectory. The direction of the trajectory is the x dot vector. That's the tangent vector. Let me draw that on a picture here. So here, this vector, this is x dot. The x dot can be calculated exactly given the current position and the current time. So given the current value of x and the current time, you can always calculate the tangent vector at that specific instance, and you just follow that direction. That's it. Right? You just follow that direction for a very small time period, infinitesimal time period, and then As a result, a new location is reached, and you're going to repeat the process. Okay, calculate a new tangent vector, and you just move along that trajectory. And of course, this way you generate a flow. A flow, a trajectory, is just a solution to a system of ODEs. Okay. The exact solution formula for this system does not matter, although we will cover it in our bridge course, promised bridge course on ODE. But the intuition is quite clear. Right? The ODE itself defines a vector field, a time-dependent vector field in general. And given initial condition, under fairly general circumstances, you can trace out a trajectory. The flow is the trajectory whose derivative matches the vector field. Exactly. Okay, so Christian is answering a question. So vector field is a bunch of derivatives at every point, and if we have an initial point and we follow the derivative and we got the trajectory for that specific initial point, yeah, you're pretty much right. And Christian's perspective is also pretty good. I don't find any of them to be objectionable, right? So yeah, starting from initial position, which is known, you know where you should go. You know where, in which direction, and how fast you should go at that instance. Right? And let's suppose you follow that direction for a very small period of time, and as a result, you arrive at a new location. So at the new location, you're going to recalculate your tangent vector, and you then follow that tangent vector, and that's a discretized process, right? That's a discretized process, and imagine if you shrink down the time interval length, you get a smooth curve like this, and that's a trajectory, which is also called a flow, I believe. All right, so let's continue. Okay, let's continue with the exposition here. So this ODE, you have a vector field, initial condition. And here, this is the definition of flow, all right? So what's a flow here? A flow, and see how it's different from everything we defined earlier. So equation 1a, which is the ODE, requires that the derivative of x of t is specified by the direction given by u of t, the vector field. Yes, we explained that. And equation 1b requires that we start at initial position x0 at time t equals 0. Okay, so we also know that. That's the initial condition. We may now ask, if we start at x0, right, big x0 equals little x0 at t equals 0, where are we at time t? What is x of t? The question is answered by a function called flow, which is a solution to the ODE, right? Basically the trajectory. Did we say that? Hang on. The trajectory is a little bit different, no? The trajectory is, I see. So the trajectory is not, is a function of t only, but the flow also depends on the initial condition. So it's a switch in perspective. Right? It's a switch in perspective. So the main variable here, the main variable in the trajectory is time. Right? The main variable in the trajectory is time. It's the point is the emphasis is that x gives you, the function x gives you the position at a prescribed time. That's trajectory. But for flow, okay, based on the notation, the flow is a function of two arguments, really, the initial condition and the time, right? And time. So basically, you're now treating the initial condition as a variable itself. Okay, so starting from x0, the trajectory may look like this, and starting from x0 prime, so to say, the trajectory may look like this. So now you're allowed to choose your starting point, and that's actually the primary variable in the flow. Does that make sense? Right. So phi is a function from Rd times 0 to 1 to RD. Right? So it takes a pair, x0 and d. x0 is just a point in RD, and t is a specific time. It tells you, given the initial position is x0, what location you're at time t, written by, denoted as psi t of x0. So that's the ODE, and you have the flow initial condition. All right, so there's not an awful lot of difference from what we have earlier, but this is a new notation, so let's put it down in our note. So flow. So let's first describe it verbally. So flow psi t of x0 is or should we say is the position in RD at time t, which is in 0 to 1, given initial condition x0 in RD. That's flow. So therefore it would mean that d over dt psi t of x0, all right, equals ut, following our notation earlier, evaluated at the position psi t of x0 with initial condition psi 0 x0 equals x0. That would make sense. All right. So anyway, it doesn't matter which verbal description that you pick to aid your own understanding. I think you can always come back to this example of a damp oscillator, right? And as also as I promised earlier, we'll do like a bridge course on ODEs, and we'll put special attention on how to solve linear ODEs like this one, okay? Which is very important for other things we do, like the SDEs and optimal control. So anyway, so that's a flow, right? So that's a flow we just looked at. Overall, so the given initial condition x0, a trajectory of the ODE is recovered via the formula x of t equals psi t of big x0. Therefore, vector fields, ODEs, flows are intuitively three descriptions of the same object. Right? Vector fields, ODEs, and flows are intuitively three descriptions of the same object. Vector fields defines an ODE whose solutions are flow. All right. As with every equation, we should ask ourselves about an ODE. Does the solution exist? And if it's unique, well, that's basically that's a topic in the theoretical investigation of existence and uniqueness of solutions to ODE. I mean, you do have a fairly general guarantee that this will happen. A popular condition is given by the so-called Pickard-Lindelof theorem, I believe. So that's a little bit technical, but basically it says if u of t, this vector field is, it doesn't grow crazy. It doesn't grow too crazy for all values of x. Okay, so the size of growth of u is in a sense can be controlled by the growth in x of t. It's called the Lipschitz condition. It's called the Lipschitz condition. But anyway, we're not going to get into that. It's not super important. Okay, it's a very technical subject. I mean, if you want to do existence and uniqueness of differential equations, then that's a deep rabbit hole. But basically, this is what it's about. Okay, so that's a pretty intuitive picture. So a flow psi of t, here. Actually, you see, this is quite interesting notation. We are actually suppressing the time variable here. Perhaps here in this point of view, we are considering for fixed time Okay, we're considering at a fixed time t, where does the vector field take initial position x0 to? Right, so let's considering try to animate this in your mind. So we have a bunch of initial conditions like this one. Okay, so first let's draw a bunch of grid lines, just regular rectangular grid lines, which are a collection of points, obviously. Right, and at these points, you can calculate the tangent vectors. You can calculate the tangent vectors, the tangent vectors given by the vector field. You can calculate the value of the vector field at all of these positions, at the grid points. All right. But of course, the vector field isn't just defined at these grid points. They're defined all over the place. We're just selecting a bunch of sample points here. And what happens next is that, say, we're interested in, say, after a fixed time t, where do all of these initial points end up? Where do all of these initial points end up? And what's the new tangent vector? So as you can imagine, the original coordinate lines, which are rectangular in shape, after some time evolution, becomes curved like this. And here, the original intersections are at these new locations, and you have their new tangent vectors. A flow is defined by a velocity field. Here, t is a constant, and we are only considering, say, the action of the flow on initial positions. All right, so here, this is what we're doing. Okay, the flow is treating the initial condition as a primary variable, not time. Okay, trajectory, however, for trajectory, we're suppressing the initial condition and solely considering time as the only variable. So for a flow, the primary variable is the initial condition, and time can even be suppressed. Okay, so here we're considering after a fixed amount of time, different initial conditions gets carried to a bunch of new positions. And what we care about is this particular action here. How does the flow changes the initial conditions? All right. So basically, it's called a diffeomorphism. It's called a diffeomorphism. All right. So this is the concept in differential geometry. So basically, all right. Okay. So here we have the flow. The red square grid is defined by a velocity field, ut, visualized with the blue arrows, yes, that prescribes the instantaneous movement at all locations. Here d equals 2. We show 3 different time t. As one can see, a flow is a diffeomorphism that wraps space. So it's a smooth distortion of the space. Okay, so yeah, it just means infinitely differentiable. In differential geometry, the term differentiable just means infinitely differentiable in most contexts. Okay. Anyway, so here you have the existence uniqueness theorem. The proof is beyond the scope of the course. If U, remember what U is a time-dependent vector field, is continuously differentiable with a bounded derivative. That was the bounded growth condition I was talking about. All right, it's continuously differentiable with a bounded derivative. Then the ODE in 2 has a unique solution by a given flow. In this case, the flow is psi of t. Okay, psi of t is diffeomorphism for all t. Remember, what is psi of t? Psi of t is a map from RD to RD. It's a diffeomorphism. It means it is differentiable, it is invertible, and its inverse is also differentiable. All right. So yeah, it is continuously, yeah, this is continuously differentiable with a continuously differentiable inverse. I was going to call it diffeomorphism. Yes, of course, it needs to be invertible. So you can imagine it is possible to go backward in time and return this distorted state into the original, more nice-looking stage. Okay, you have a, yeah, it is possible to reverse this process. It is an invertible map for all t. It is an invertible map for all t. Okay, just think of psi of t as a family of diffeomorphism. For each t, there's different function. It's different for each t. It's a different function from Rd to Rd. It's a parametrized. It is a parametrized. It is a parametrized family of diffeomorphism for each t. When t equals 0, of course, nothing happens because there's no time evolution, right? And yeah, this is t equals 0. Say this is t equals t1, and t equals t2. All right. For each of these t values, psi of t equals 0, psi of t equals t1, psi of t equals t2, they're all diffeomorphism. This is a collection. This is a parametrized family of diffeomorphism. The parameter is exactly the time parameter in the ODE. Okay, hopefully that's a intuitive enough introduction to ODEs. All right, we'll do like a bridge course to ODE sooner rather than later. All right, so here you have the fundamental existence uniqueness theorem is proved using a real analysis. You need some background in, for example, you need some background in sequence and series of functions or contraction mapping, that kind of stuff, to prove it. But let's just take this result for granted, which is, I don't think this will cause any harm at all. Okay, yeah, just take this result as granted. Note that the assumptions required for the existence uniqueness of a flow are almost always fulfilled in machine learning, as we use neural networks to parameterize. Okay, you use neural networks to parameterize what? To parameterize ut of x. And they always have bounded derivatives. So here we are representing or approximating the vector field using a neural net. So basically, this is once again a very high-level description, all right? So a neural net, in case people in chat are new to this, a neural net is you can think of as a super powerful function approximator. Okay, so that's a neural network. Okay, so it allows you to approximate a function extremely well. So in reality, you might not have the exact vector field, as we did for the damped oscillator model, okay? But you can still approximate the vector field rather well by using a neural net. So this is now represented by a neural net, okay? Exact details is a black box, and that's fine. The neural net is a powerful approximator. It's like linear regression on steroid, basically. Okay. All right. So here we have an extra ingredient, right? So first we introduce ODE and the idea of a flow. And what's the idea of a flow? Actually, let's write it down here. We didn't write that down. Here we have ODE, initial value problem, trajectory, and what's the flow? Right? Oh, actually, we wrote that down. Right. So a flow at for given t is psi t that maps from Rd to Rd. So for different types of neural net, it's different method of approximating. Exactly. You are completely correct. right? The exact details don't matter. So basically, we're just considering a well-approximated version of UT, because quite common in practice, you don't have exact information of the vector field. Right. And is assumed to be a diffeomorphism. And this is justified based on the qualitative theory about ODEs. Okay. So this is assumed to be a diffeomorphism. All right, so let's take a look at a specific example. And we're learning the vector field via neural network, and ODE solvers who get to the trajectory, yes. So how is this different from ODE solver? Good question. I mean, I haven't get to that part yet. I think ODE solver will play a part. Say like the book standard Euler's method will become useful. Because we haven't even discussed how we're going to solve this, right? We just theoretically described the trajectory. We haven't even touched on how the numerical solution is obtained. But we do have one ingredient being added into the mix. That is, the vector field is now approximated by a neural net. Right? We haven't said anything about how the trajectory is obtained or how the flow is obtained. Okay, and perhaps the flow itself will be represented by a neural net too. And let's see if that's how it's going. Okay, so basically, theorem 2 should not be a concern for you, but rather good news. Flows exist and are unique solutions to ODEs in the case of our interest. A proof can be found in, well, probably Baby Rudin or some textbook on. Actually, I'm interested. Which book on ODE is quoted? I'm guessing. Okay, I'm guessing that would be my guess. It would be Coddington and Levinson. I'm guessing. Okay, my guess would be Coddington and Levinson. Spoke classic text on ODE called The Theory of ODE. Let's see if that's the case. We go to 32. Oh, actually, this is another classic by Perko, Differential Equations and Dynamical System. This is also a very nice book. Okay, perhaps at some point we'll look at qualitative theory of ODEs too. Very, very, very fascinating subject. Yeah, there you go. 9 is indeed Coddington and Levinson. Oh, actually, there's a third author too. I didn't know about that. Theory of ODE. Extremely well-cited book. Anyway, I'm just name dropping, and please forgive me for doing so. We don't have time to do details of ODEs. All right, so I think we're getting close to the diffusion model, which is nice. Here we have the first example, right? It's a simple example. This is perhaps the most basic, non-trivial ODE you can think about. That's the exponential decay. Right? That's exponential decay. So if you have, say, just R1, right? Just a single scalar variable as your x. So I mean the vector field can then be visualized this way. So this is the x-axis, all right? This is the origin. The vector field is what? Is minus theta x. So theta is positive. So therefore, for positive x, the vector direction points left. It points towards the origin. And when x is negative, u would be positive. Therefore, it points towards the right. So that's the 1D vector field. This is the 1D vector field. And the solution, of course, should I derive that? Or is that too basic? X dot equals minus theta x. You can solve this in a variety of ways. For example, we can solve it using the separation of variable method. That's dx over dt equals minus theta x. By separation of variables, you get dx over x equals minus theta times dt. and you integrate d over dx over x equals minus the integral of zeta dt. This gives you the natural log of x absolute value equals minus zeta t plus big C, and then exponentiate both sides. You get x equals by a abuse of notation in the constant, it would be c times e to the minus zeta times t, and using the initial condition, x naught equals, well, x naught, then c should be x naught. So that's the solution. So that's the flow. All right, so that's the flow. So if you want to plot the function here, you can do so this way. Assuming that t is a constant, right? Assuming that t is a constant, then the flow is just a linear function in x naught. The flow is just a linear function in x naught. So x naught is the x-axis, and this is psi of t. And this is psi of t. So yeah, so this should be a linear function with a positive slope because the exponential function is positive. So that's basically the flow function. All right. So yeah, and you can check this, right? You can check this easily by differentiating. I'm not gonna do this. Okay. So in figure 3, visualize a flow of this form converging to 0 exponentially. Here we have do we have the picture? Figure 3. Figure 3. This is figure 1. Figure 2. Hang on. This is figure 2. This is stochastic process. Yes, this is figure 3. What? Why do we even have a? Okay, we don't have a stochastic process. We're not even there yet. Okay, this might need to be changed. This might need to be changed because, okay, anyway, I don't think we should have any problem with this simple ODE. It's just a basic exercise in calculus, all right? Of course, in general, it's not possible to compute solutions analytically. It's, in which case we use numerical method. It was the leftmost graph. Hang on. You mean this one? But this is OU process. Well, I guess you can say OU process when sigma equals 0 is exponential decay. But this is trajectory, right? This is trajectory. The flow, remember, we emphasize the difference between the flow and the trajectory. Trajectory is from t maps to xt. And a flow is what? A flow is x naught to psi of t of x naught. Right? So it should be a function of x naught where we treat t as a constant. Right? And based on our solution earlier from the example, not a great figure to refer to, I know, right? Because this can easily cause confusion. Let's say if you're just reading the main text and you don't even know what on earth an OU process is, this would cause confusion. Of course, this is still valid, right? Mathematically speaking, although I don't think that's great organization. But anyway, I'm pretty lenient when it comes to writing, just because I know how difficult it is to write mathematics. But anyway, here we have this actual representation of a flow, because the flow is a function of the initial condition, and we know that here this is a linear function in the initial condition, so this is x naught and this is psi of t, a psi parameterized by t. Assume that t is a constant, and this is just a linear function. It's just a linear function in x naught, and the slope is always positive. The slope is always positive. So here, for example, for a specific value of t, it's just a linear function through the origin, like this. And as you can see, as t grows, the slope gets smaller. So this is for t small, and this is for t large. Both represent flows at different point, at different time. All right, so that's the, that's basically the ODE model here. Of course, you should, in general, solve the ODE using the numerical methods. And of course, fortunately, this is a classical and well-researched topic in numerical analysis, and a myriad of powerful methods exist, right? So Alpha Chloe, Chloe was asking, how is this different from an ODE solver? Well, the ODE solver is being called for. The simplest method is the Euler's method. Let's see what this means. How is this so basically in an ODE, numerical ODE, okay, so let's do a little brief section on numerical ODE, which is, of course, a topic worth its own series, worthy of its own series, numerical ODE. So x dot t equals ut of xt, right? So that's the ODE itself, and with initial condition, x of 0 equals little x of 0. Okay, so that's the ODE problem. And we're going to approximate the trajectory by discretization. Okay, approximate the trajectory via discretization at time t naught, which equals 0, less than t1, less than t2, all the way to less than t, say tn, which equals 1, right? That's the final time. Okay, so imagine you're going to, this is the continuous trajectory, 0 to 1, and you're going to approximate this smooth curve by a polygon. So this is x1, x2, and whatnot. All right, so that's basically what you're getting at. You want this approximation. So how do you do that? How do you construct such approximation? Well, the ODE can be, the ODE actually, yeah, so the ODE including the initial condition can be reorganized or reformulated into an integral equation. So you can integrate both sides. Okay, integrate both sides from 0 to t. Actually, that's from left to right. You can integrate the ODE from 0 to t, and this way you get xt minus x naught equals the integral from 0 to t us of x of s ds. And of course you can rearrange the term and put plus x naught to the right. So that's it. This is an integral equation. Of course, doing this does not seem terribly helpful because on the right-hand side you also have the unknown function. But the thing is, it tells us that you can approximate the solution by approximating the integral. So we're just going to approximate integral. You can use various approximations for the integrals, which leads to different methods for approximately solving the ODE. That's the idea. The overarching idea of solving ODEs numerically is to approximate this integral. So that's why solving ODEs is also simulating ODEs. Simulating solutions to ODE is also called integrating an ODE. Okay, so basically we can approximate the integral using various schemes, such as you can. Okay, so here I'm just going to write it this way. For say for k equals from 0, for k equals 0, 1, all the way to big N minus 1, little n minus 1. We have x of t let's write, how can we represent the approximate solution? Let's write x hat. Okay, x hat is the approximate solution. Approximate solution x hat at let's write, okay, let's write x hat of k to be the approximate value of little x, big X, right? Big X at time tk. This is what we mean. Here you have x hat of k plus 1 equals the initial value. The initial, here I'm only considering a small time interval. Okay, so consider, let me just write it this way, consider the time interval. Consider going from tk to the next time position, time instance to tk plus 1. So the approximate value x hat k plus 1 should be, looking at the integral equation, that's xk hat plus the approximate value of the integral. The integral hat from, let's write it this way, integral hat, okay, integral hat, that's the approximate integral sign, okay, I made this notation up. The approximate integral from time tk to tk plus 1 of u of s, x of s, ds. This is the exact relation. There's no approximation here. But of course, the problem is we do not know the values of big X where s is between tk to tk plus 1. We have no knowledge of x of s in that time interval, and therefore this must be resorted by some kind of approximation. So you can use different approximation. Approximately, you can use the left-hand rule, right? You can use the left-hand rule. So for example, you can evaluate big X at the initial position, which will give you us. This is the most straightforward way to, the most primitive, right? That's the classic Euler's formula, Euler's method. U of s, x of tk, in which case we don't know that exact value either. We have to use an approximation. So we'll do a second step. Right, so multiply this by delta tk. Okay. Here I'm going to write delta tk to be defined by, usually that's a fixed value. Okay, that's a fixed value. Actually, you know what? I'm just going to use h. I think h is the notation used in the course note. So h is the constant. Okay, is the constant that is the size of the time grid, basically. So you have tk minus 1. All right. So times the length of the time interval, which is h. All right. So that's the left endpoint approximation, and then you're going to approximate that even more by writing u, here, let me just change that, s is also changed to tk, okay? So u of tk evaluated at x hat k, further approximation times h. And this is the Euler's method, the classic Euler's method. All right, so let me change and move things around here. So it all boils down to how to approximate integral. And after you've done that, you suddenly realize, oh, the right-hand side can now be readily evaluated. The right-hand side can now be readily evaluated, right? So this is x hat, okay? And here you have u tk evaluated u hat, utk of x hat of k times h. So this is called the Euler's method, and more specifically called explicit Euler's method. And why is it called explicit Euler's method? Because you can just use the iteration at step k and perform a direct evaluation on the right-hand side to get the next iteration. And this is an explicit evaluation. It requires no equation solving. It's just a direct substitution. And that's why it's called explicit. And this is to contrast with the so-called implicit Euler's method, because in an implicit Euler's method, you would use the right endpoint rule, right, or the right Riemann sum, whatever you want to call it. That means you're going to use the time instance tk plus 1. So instead of utk, you get utk plus 1. Evaluated at xtk plus 1 times h, which is further approximated by utk plus 1 of x hat k plus 1 times h. This is implicit because, as you can see here on the right hand side, you have the value of the next iteration itself. So this has to be solved by, well, the next iteration has to be obtained by solving an equation, and quite often use a nonlinear function. So this is in fact a nonlinear equation which needs to be solved at each iteration. Well, why on earth would someone do that? It seems awfully complicated because of numerical analysis reason. Okay? Because sometimes there are advantages of using, and sometimes not just an advantage, but necessity of using implicit methods. Okay? Because of, well, sometimes you have quote-unquote a stiff equations. Sometimes you call stiff equations, and explicit methods can lead to very false results for stiff problems. Basically, that is, roughly speaking, there are drastically different time scales existing in intrinsic to the system, and this is often quite the case for ODEs that models chemical reactions. So sometimes in a chemical reaction where you have a number of reactants, reactions can happen at different time scales. So some reactions are very fast. Okay, the kinetics or mechanisms are different. So sometimes certain reactions can happen super fast, and sometimes and at the same time, okay, certain reactions in the system happen super slow. And that way you get a quote-unquote a stiff system. For a stiff system, you have to use implicit Euler method, just a different option. And for that, the price is to solve a nonlinear equation, as we mentioned, at each iteration, but you're getting advantage of stability. And of course, you can also use the midpoint rule. You can also use a midpoint rule, which would be, right, which would be an average of the two endpoints. Right? That's a trapezoidal rule. Right? Just regular calculus techniques now being applied to integrating the ODE. So that would be h times the average, that would be half of u of tk evaluated at x hat k, and then plus utk plus 1 evaluated at x hat k plus 1. And that's the trapezoidal rule. Let me draw the picture here. So this is the time instance tk. This is the time instance tk plus 1. Remember, we're approximating the continuous curve by a polygon, right? By polygons, and therefore the area, the exact area, is approximated by the area of a trapezoid. Okay, so that's the average here. That's a trapezoidal rule, and as you can see, the trapezoidal rule is also implicit, because the value of the next iteration also appears on the right-hand side. Right. So these are all very classic integrators in the theory of numerical ODEs. So Chloe, yeah, classical integrators, ODE solvers is useful here. Like these are all examples, by the way. These are all examples of the family of ODE solvers called the Runge-Kutta method. Runge-Kutta method. All right. So Runge-Kutta method basically allows you to approximate the integrals. This integral. So, I mean, actually, all ODE solvers are boiled down to approximate this integral. Okay, with fancier and fancier ways. Okay, and there's quite a lot of intricacy when it comes to the numerical characteristics of these integrators. These are all, they all belong to the families of Runge-Kutta method. Okay. So that's numerical ODE in a nutshell. And you have some well-developed theory and packages for those things. Okay, this is Euler's method. It's forward Euler's, or the explicit Euler's method. That's the update rule. H is the step size. Because remember, the total length of the time interval is 1. So H is 1 over n. N is the number of simulation steps. For this class, the Euler's method will be good enough. You can have more complex methods, such as Hume's method. And this is called the, I think Hume's method is the same as predictor-corrector method, right? Yeah, it's the prediction. You use it has 2 steps of calculation here. You're first going to predict the next value using the Euler's method, and then you're going to make a correction based on the trapezoidal rule. And you can combine all these different methods of approximation based on what we discussed earlier. Okay, so yeah, and you can just one example. Okay, so that's not terribly important here. Okay, the main takeaway is that given the existence uniqueness here, given the result of theorem 3, you can a variety of methods to integrate ODEs are available. These are all very well researched topics here. Okay, so not a terribly exciting topic to talk about, but here finally we're getting into the main technique here. What is a flow model, and how does that even related? How on earth is that even related to sampling? Okay, this is where things get super interesting, because overall, like here, from the introduction of ODEs to the definition of flow and the numerical simulation of ODEs, these are all classical methods, right? Classical, well-known stuff in applied mathematics. You need to learn this too. You mean ODEs? Yeah. I guess some basics would be necessary. And I said I will give like a bridge course on ODE because it's being used in so many different things that we've been doing on the channel. A bridge course in ODE, including some basic numerical methods, would be necessary. Analytic solutions to linear systems, transform methods, some basic idea of proving existence uniqueness, as well as numerical methods are probably going to be in the curriculum. Anyway, so so far, this entire block of material from here all the way to here bears nothing that connects to what we discussed in section 1. Okay, this whole big section on ODEs has nothing to do yet with the main problem of interest, that is generation of of objects, quote unquote objects, right? Remember, what do we want? We want to sample a realization from the data distribution. At this point, we haven't said anything about that whatsoever in section 2 yet. Instead, we were the SD or the SPD aspect of interest. We haven't got into that part yet. We're still discussing ODEs, okay? SDEs, as we covered in our earlier SDE session, is basically ODEs with noise. Here there's no noise, okay? It's just purely deterministic dynamical system described by an ODE. Okay, but we have not yet discussed any kind of connection between ODEs and the sampling problem or generation problem. Right? Generative AI. I'm 3 hours behind. What do you mean? Like we started at 7, right? Yeah, we started at 7, so that's what you mean by 3 hours behind. Well, I guess you have to catch up with the earlier part. But basically, Nadia, I will give you like a short recap. Okay, it will take like 5 minutes to do so. So the data, okay, in a nutshell, so the data we're considering are images, videos, things like that, which are mathematically represented as vectors in our D. Right? D is typically very large. All right, and the generation problem is a sampling problem essentially. So we're assuming that the object of desire, such as an image of a dog, follows a distribution over the data space whose density, the probability density, is P data. And the generation problem boils down to selecting a realization of the data distribution. That is to say, you want to generate a random observation, random realization of the data distribution. That's what we want. Right? And here, because typically you don't know the exact data distribution, you would need a data set to learn it. Right? But we're mostly concerned at this point with the generation problem. For that, we're going to assume that P data is already known, and we are interested in how do you generate stuff from it. Right? Monte Carlo simulation in computational statistics on its own is a well-researched topic. Well, of course, it's still growing, but it's a well-researched topic. But I think we're doing things somewhat differently in the context of generative AI. We're going to do the generation using quote-unquote the flow method and the diffusion model. Right? The flow model and the diffusion model. So that's what we're going to. All right. So next up, well, we just described flow, self-contained, relatively speaking, introduction to the fundamentals of ODE, and now we're ready to connect with the flow model. Okay, so Nadia, that's kind of what we did in a nutshell. I did that in a less than 5 minutes, I believe. All right, so let's continue. Flow models. We can now construct the generative model. I do wish to, because I want to do more, let's say 2 hours until 12, and hopefully by that time we will reach at least a mathematical definition of a diffusion model. Okay, not just on a vibe level. Okay, I want to get to actually the definition of a diffusion model. So the flow model. Okay, what do we mean by a flow model? We can now construct a generative model via an ODE by making the vector field a neural net, a neural network. A neural network vector field. That's crazy. That's crazy. So far, we've talked about nothing about deep learning or nothing like that. The ODE, of course, we said earlier that the ODE, the vector field, and the flow are in a sense all equivalent. If you know one, you know the others. Right? And that's one of the main messages. One of the main messages in this self-contained introduction to ODEs. Vector fields, ODEs, and the flows are intuitively 3 descriptions of the same object. Right? And here, the vector field, which is U, is going to be represented by a neural network. We can now construct a generative model via an ODE by making the vector field a neural network. A neural network vector field U theta t. For now, we simply mean that U theta t is a parameterized function. RD times 0, 1 to RD. Remember, that's exactly how we defined the vector field earlier, except now you have some parameters in that function. Let's say the form of the function is specified. It's just that the unknown parameters are there for you to, I guess, to learn. I don't know. I don't know yet. Okay, neural network typically needs to be trained, right? But basically here, you have UT earlier here. U is from RD times 0, 1 to RD. RD is the position. 0 to 1 is, well, the time parameter. And RD is the tangent vector. It tells you what's the next direction the trajectory should follow and how fast it should go. Right? So that's a vector field here. And here we just assume that that vector field is represented by a neural net. Now, remember, earlier, at a very high level, we introduced neural net as a super powerful function approximator. So this is a proxy for the exact neural net. This is a neural net is a proxy, a surrogate for the exact vector field. Okay, so from RD times 0, 1 to RD again, with parameters theta. Theta is something that we can specify. Later, we will discuss particular choices of neural network architectures. Okay, so that's just a specific detail that will be finalized later. Perhaps there's a bunch of choices, typically, with pros and cons for each option. But basically, this is what we're doing. We're representing the vector field by a neural net. Remember that our goal was to generate samples from a distribution P data, right? So Z follows P data from a distribution P data. So how can this be done? In particular, these samples must be random. Note, through an ODE itself is not random but fully deterministic. Exactly. To inject some randomness, we simply make the initial condition x naught random. Okay, so basically here we had a visualization for the concept of ODE. Right? This is our vector field. Right? This is our vector field, but the initial condition x naught is just a point in RD. You're going to randomize the initial condition. And for a given initial condition, the resulting flow is completely deterministic. Remember, the deterministic function psi t of x naught is the flow. It's just that the input x naught is randomized, and as a result, the output is randomized. But it's just a diffeomorphism of a random x naught. Okay, seems to be the idea here. Okay, so specifically, if we choose initial distribution, P initial, in most cases we set P initial to be well, just a standard normal distribution. This is an IID normal distribution with dimension d. Right, this stands for the normal distribution, and this is 0. Mean is 0. And ID is a covariance matrix. So basically, this is the same as saying that you can write it this way. So x naught, this is x naught. Remember, this is x naught is a vector, right? X naught is a vector. So you have x naught 1 all the way to x naught d with x naught I being IID, normal, 0, 1. These are all standard Gaussian distribution. Okay, so that's the initial condition. I don't think there's anything special to it. It's just a simple initial condition. Most importantly, whatever initial distribution, whatever distribution you choose, it must be one that we can easily sample from an inference time. At inference time. Hang on. What is the inference time? What's inference time? So basically, all right, so let's draw a new picture, all right? So we have the ODE. We have the ODE, so now we're going to, okay, do some quick notes here. So this is a flow model. The fundamental ingredients of a flow model. So the vector field, vector field is a neural net. All right, so yeah, so it takes RD, which is, this is the initial condition, times 0 to 1, that's time. Okay, and to RD, that's another vector. This is a tangent vector. The vector field vector, if you can call it that way. This is a vector field vector. Not standard terminology, but, and it's kind of awkward to say, but it shouldn't be ambiguous. All right, so that's the vector field. The vector field is a neural network. The neural network, parameterized by theta, by the parameter theta, the parameter. Parameter theta. And of course, the ODE, right? This is, as we said earlier, this is equivalent to an ODE and also equivalent to flow. In a sense, they're all the same object, right? And we're going to randomize the initial condition. The key idea here, is we're going to randomize initial condition. How can we visualize that idea? Okay, how can we visualize the idea of randomizing initial condition? Well, let's just maybe put it this way. Okay, so this is the flow function. This is the flow. This is the flow. All right. So this is psi of t from RD to RD. So let's draw two coordinate system. Here, this is RD. This is RD, and we have another copy of RD, like this. So you can think of the flow, right? The flow, as we mentioned, the flow, it's a map that takes initial conditions to new, it maps initial conditions to new position, new location. And in the notes, we call that a space wrapping or a space distortion. That's a flow. This is a flow. I'm trying to replicate this idea here. So, okay, so the initial condition is now randomized. Let's do that. Let's visualize that by drawing some contours on the left coordinates. Right. So you guys probably seen bivariate normal distribution, right? Which is usually visualized as a bunch of concentric ellipsoids. Right. So that's a visualization of a Gaussian distribution. In the case of say IID Gaussians, the equidensity contours would be just circle center at the origins. At the origin, right? So that's a P initial here. So P initial here, just imagine how these contours are transformed, or twisted and compressed or expanded because of the flow. So you might get something like this. Some complicated looking shape. Right? Remember, the ODE is defined by the vector field. If you know the vector field, you know the ODE, and if you know the ODE, you can integrate and you get the flow. And now, instead of just considering the trajectory of a single initial condition, for a single initial condition, you're considering, okay, the flow as an object that transforms RD, that maps subsets of RD to another subset of RD, that carries a subset of RD to a subset of RD, right? And the initial distribution is now visualized as a bunch of equidensity contours in the left copy of RD, and after the flow, after the action of the flow, it gets transformed in these new contours. All right, so that's P initial. And what is this? Well, hopefully this means something, right? This transformed version of P initial, because this is a well-known type of problem in probability theory, in principle, right? Given some initial distribution, and you apply invertible transformation to it, and you can get a new density. Right? This is a well-studied problem in probability, and there's actually very well explained examples. Perhaps I'll go to my go-to source on basic probability and statistics, which is the book by Evans and Rosenthal. Right. It's been a while since we looked at this one, but basically, I think we can look at the preface. All right. So just give an example. I'm just telling you that given initial distribution and you apply a diffeomorphism to it, you get a new distribution. This is a well understood problem in elementary probability. Where's the? Hang on. Where's the? Okay, I need the list of content. Yeah, just a single PDF file makes things easier. Yeah, there's even an analytic formula for that problem. The key is to use the Jacobian of the transformation. Hopefully, the audience is familiar with that problem. And here we have joint distribution, conditioning and independence, multidimensional change of variable. Yes, that's exactly what we're talking about. It's continuous case, 110. It's called advanced because this course offered by U of T is usually offered at the same time students typically take Calc 3 or 4. So that's why it's considered advanced. Multivariable calculus stuff is considered advanced for this book. 110. Page 110. All right, right here. This is a discrete case. We don't care about that. Yeah, this is a continuous case. So this is a well-known problem. This is only a two-dimensional problem, but the principle extends to n-dimensional in the exact same way. So suppose you have a jointly distributed random variable, x and y is a vector. Okay, x and y are both scalar random variables. And it has original, that's the old density, f of x and y. That's the initial distribution of x and y. You define a transform version, that's z and w. And this transformation from x and y to z and w is invertible. All right, so this is an invertible transformation. Assumed to be differentiable is a smooth transformation, is invertible. All right, so we want the new distribution. So we want the distribution of z and w, and this is given by this formula. And the answer is given by this formula. The new distribution, the distribution of the new variables z and w, is given by the old density. Of course, the old density has arguments x and y. You have to represent, you have to solve for x and y in terms of z and w. So that's basically the old density, but now just in terms of z and w, times or divided by this Jacobian. Divided by the Jacobians, right? This way, this is basically a simple application of the change of variable formula from multivariable calculus. So here in our context, x and y together as a vector follows the initial distribution, P initial, and the transformation big H, little h, is the flow. Hang on, is the flow. Is the flow from R2 to R2, here from RD to RD. And the new distribution, is, well, is an answer to a well-known problem. Okay, and okay, let's see. I mean, this is a well-known problem, but let's see where this is going. After all, we want to sample from P data, right? Our initial distribution P initial may have nothing to do with P data whatsoever. It's just a random guess. It's just the initial distribution, which may or may not have anything, and most likely has nothing to do with the actual P data. But how can we bring P data into this business? Okay, but basically here we just describe a well-known problem in basic probability, right? The transformation of a continuous distribution via one-to-one smooth transform. Okay, so here the idea is we randomize the initial condition. Right? Randomize the initial condition. Most circumstances, most cases, you just pick the initial distribution to be a spherical Gaussian. This is what we call a spherical Gaussian. Isn't that similar to the CDF method? If the CDF method is actually more general, because the CDF method doesn't have to apply to invertible transformation. All right, you can derive the Jacobian method, which we just talked about, from the CDF method. You can do so, but CDF method is more general. Should I just follow the current time and rewatch? You should follow the current time because I just gave you a recap of what we just did. I think you can follow what we're doing by just watching the real-time version of the stream. Okay. All right. So here you have random initialization and the ODE. Our goal is to make the endpoint. Our goal is to make the endpoint x1 of the trajectory to have the distribution of P data. So our goal is to make this P data. But how on earth can you control that? How on earth can you control that? Huh? I mean, in this problem, in this section already, in this section, we assume that P data is known. Here, earlier, we have our workflow, our conceptual workflow. You go from data set to data distribution and then to output, right? Here we're only worrying about the second half of the workflow. You have the data distribution. How do you get an output? How do you simulate? How do you generate? Whatever you want to call it. How do you sample? Might need to be told in text chat as we're still 2.5 hours behind the current live stream. Yeah. So Nadia, just to summarize what we did. Okay. And for follow current. Yeah. So you have a P data. How do you sample an output from it? How do you sample a realization, a data point from P data? That's what we care about, okay? And we do that in a very ingenious way, okay? You start from an arbitrary initial distribution. Typically, it's just a spherical Gaussian. And you want to create a time evolution that maps from the initial distribution to data, to p data. Right? So you want to create this this diffeomorphism. All right. So how do we do that, though? This is still very unclear now at this point. It says our goal is to make the endpoint x1 of the trajectory to have distribution p data. So you want p x1 to follow from p data. P data is the distribution that you care about. Remember, you want to sample from p data. You want to sample from p data, and this is the same as saying the flow given the initial condition x0 follows p data. So basically, going back to our theorem here, right? Going back to our theorem here, we don't know the h here. We don't know h. Guys, we don't know h, but we know the initial distribution, which is just a convenient choice, and we know p data. Assuming, I don't need I don't need this. Leave me alone, AI. God dang it. So here we have this formula. We have the initial distribution, fxy. And we also have the transform distribution. Here, in this theorem, in elementary probability, the application of theorem 2.9.2 is as follows. You know the initial distribution, and you know the transformation, and you're interested in the new distribution. Let's look at an example, for example. I'm pretty sure there's an example here. Yeah, you can see here, this is old density. And here you have a transformation, z and w, in terms of x and y. And you want the joint distribution of z and w. That's a typical setup in elementary probability. But now, things are a little bit different. Okay, we know p data, which is the output here. We know the left-hand side. And we know the initial distribution. We know the initial distribution, f of x and y. But we don't know the transformation. I think the goal here is to approximate h using a neural net. Because after all, right, the vector field, is equivalent to the transformation, h. Right? So you're describing u as a neural net, describing u, which theoretically speaking also defines h. So you're going to tweak h so that you approximately have this transformation formula hold. I believe that should be the idea, but let's check our intuition. Okay, so let's go. This is our goal. Our goal is to make the endpoint x1 of the trajectory to have the distribution of p data. Right. So now, I think earlier someone asked, why is the time value 0 to 1? Why is the time value 0 to 1? Because the endpoint, well, you need a finite endpoint because you don't want 0 to infinity. Right? You want the endpoint to represent, right? To endpoint, and at the endpoint you should recover or obtain distribution of interest, right? You want to draw distribution from p data. Here, p data should be, right? Our goal is to make x1, the endpoint of the trajectory, to follow distribution p data. Okay, so if we have to draw this on a single picture, I guess you can superimpose. The two diagrams, but I think that would be too messy, right? I think that would be too messy. But basically here, if I'm going to add 2 more points, this is x here. This is x0. Okay, this is x0, and it gets mapped to somewhere here. Like here. This is psi of 1. Psi 1 evaluated at the random x0. This follows p data. So hopefully this is a clear conceptual diagram. All right, let's go. Okay, so here, where psi theta t describes the flow induced by the vector field. Yes. Note, however, although it is called flow model, the neural network parameterizes the vector field, not the flow. Exactly, right? The neural network parameterizes the vector field, not the flow itself. In order to compute the flow, you need to simulate the ODE. In algorithm 1, you summarize the procedure of how to sample from a model, flow model. Okay, let's try to analyze this. Algorithm 1, sampling from a flow model with Euler's method. This is box standard ODE solver. It's as simple as possible. Okay, nothing fancy at all. Just the Euler's method. No implicit method, no Runge-Kutta, no nothing. It's just Euler's box standard Euler's method. So you start with a vector field. Parameterized by a neural net. Okay, so assume this is all known. Okay, the neural network is known, and you also specify the number of time steps and what we want. Well, we want x1. We want x1. So you just follow the Euler's method. This iteration, this explicit Euler's method. All right. So what do? You start from initialize the time. Right. The time step size is easy, just 1 over n. You draw a sample, draw a random sample x0 from the initial distribution. Initial distribution is given. In most circumstances, it's just a simple standard Gaussian, or spherical Gaussian, as I like to call it, because the covariance is spherically symmetrical, or rotationally symmetric. All right. Anyway, x0, this is a simple simulation problem. Right. Because P initial is very simple. So next, you're just going to do the Euler scheme. You're just going to do the Euler scheme, all right? So here, let me just put it this way. This is a continuous diagram here. This is the continuous diagram here. So let's start from this picture right here. Okay, let's start from this picture. Let's say, let's suppose now x0 is already drawn. The x0 is already drawn, and using the Euler's method is nothing but using a polygon to approximate a smooth curve, right? So basically, starting from x0, and you can just follow the vector field, you draw a polygon, maybe like this, okay, to get to the new location. So that's basically Euler's method. And you get, this is what we call the psi hat 1 of x0. The approximate solution to the ODE. Right? This is a completely deterministic process. Remember, once you're given the vector field, right? Once you're given the vector field, doing this iteration is no problem. Doing this for loop iteration is no problem. And when all the time steps run out, you get x1. You get x1. So here, there is no guarantee whatsoever in this algorithm that x1 is going to follow the p data. Right? Here we're given the
remember, to do so, let's say to accomplish that, if we want x1 to follow p data, then the transformation, aka the flow, should be highly specific. Remember, in our theorem here, let's say if you know the initial distribution and you know the final distribution, and the unknown is the diffeomorphism, you essentially have this highly nonlinear equation for H. You essentially have this highly nonlinear equation for H. You have fxy is given and fzw is given, but H is not given. H is the flow, which is equivalent to the vector field. Here, we don't know what H is, right? We don't know what H would satisfy this relation. We don't know that. But here you just start with a given. Suppose you have a given vector field, u theta of t. Doing the Euler's method is a very straightforward manner. This is what algorithm 1 says. Here we do not guarantee that x1 follows p data whatsoever. We don't have that. Okay. Okay. So next up, right? So here we just described algorithm 1. This is nothing special. This is nothing surprising here. Every Calc 1 student can do this. Every Calc 1 student can follow the Euler's method very easily. But still, the burning question is, how on earth can you have x1 follows p data? Let's go. Pardon, this is done? Are you kidding me? Are you kidding me? This is already done? Are you sure about that? How on earth is this guaranteed, man? Did I miss anything? Oh, perhaps there should be a more in-depth understanding of that. It doesn't explain at all. It doesn't explain at all. I think this is incomplete. Section 2.1 is incomplete because here we're simply just doing the Euler's method for a given vector field, right? And there's no reason that for any given vector field, the resulting, because p initial is completely arbitrary, there's no guarantee that x1 would follow the target distribution. So therefore, what I'm thinking is as following. Maybe this is wrong, okay? Maybe this is wrong. I'm just trying to connect with whatever that seems plausible. All right, so basically I was saying that because we have this well-known result, right? So we are interested in finding the right transformation. Because if you have the right transformation, can you... Okay, so this is diabolically annoying as hell. Can we... There's not even a freaking... I think it will be expanded on later, okay? I don't think there's even a way to turn this damn thing off. My goodness, it's annoying. Anyway, so let me just open up a new PDF, because I have it downloaded a long time ago. Michael Evans. Hang on. Yeah. Right, so page 110. Perhaps this will be expanded. It better be, because this is completely unclear why the final endpoint would follow the target distribution. And where's 110? Yeah, simulating continuous distribution. These are some elementary methods. Okay, no ODEs involved here. But I'm saying is, because of this general result of transforming continuous distributions, you have the original distribution. This is P initial, and this is P data. This is the target distribution, right? If you know H, if you know the transformation, like what is being described here, if you know the transformation like what is being described here, because remember, if you know U, theoretically, you know the flow. If you know the vector field, theoretically, you know the flow. Right? So that's just the explicit evaluation on the right-hand side, although with a fancier method using ODE. If you know U, I'm saying that again. U is, we can now construct the generative model via an ODE by making the vector field a neural network vector field. All right? So you have that U, which, well, is equivalent to knowing the flow theoretically. Right? In practice, the flow is approximated by the Euler's method, which brings us to this formula. If you know the transformation and the original distribution, you know the final distribution. But because of the initial distribution is arbitrary, and the neural network right now is also quite arbitrary, there's no guarantee whatsoever that the left-hand side, the resulting left-hand side, the new distribution is going to be your target distribution. You have no control over it, right? But here, the problem is we want to construct a flow. We want to construct a flow so that starting from our initial distribution, the final state, okay, the endpoint of the trajectory follows the target distribution, the data distribution. So that's what we want. So that means in this formula here, on the left-hand side, we already know. We already know the left-hand side. That's P data. That's our desire. Okay, we want P data. P data is already know. We want to draw samples from P data. We just don't know how. Okay, but we know P data. We also know P initial on the right-hand side. Pxy, it takes the place. So P initial takes the place of P of x and y here. But we don't know the transformation. The transformation H represents the flow, the psi function, the psi function, psi1 of theta. That's the flow. That's the flow. So I suppose you now have a functional equation for the transformation. Right? This is a highly nonlinear functional equation for the transformation, because the problem is we want the initial distribution to be transformed into P data. It's just that we don't know the flow. We have absolutely no clue what this is, but it should satisfy this condition. But it should satisfy this condition, which is a nonlinear equation for the transformation. And the problem now is to solve this nonlinear functional equation approximately. How are we going to do that? Well, you probably want to minimize the difference of both sides. You want to minimize this using a mean square criteria or something. Do the gradient descent. Right. Do the gradient descent. Then that's how you got the you can get the you get H approximately, which means equivalently speaking, you get the U approximately. Okay, so that would be my intuition. Hopefully, I know this is still, there's a lot of details to be filled up, but I hope this makes some sense. Okay, because the note seems to be rather incomplete here. All right, I haven't been paying attention to chat here really. Christian says, you did not. This material is simplified a lot and did not explain the details at all. Okay, which I guess probably that's why we need a book, right? This book is like 500 pages, so probably we can dig more details here. But well, as is promised in the lectures, in the course website, you should be able to build something like a flow model from scratch. I hope that's like not canned, okay? Because that's the core of this generation process. Hopefully, we'll get that covered at some point. But I mean, there's a more expanded exposition here, but well, by different authors. Hopefully, there's still some similarities between them. Okay, is there a flow model here? And this is purely SDE. Okay, there's a flow-based perspective, normalizing flows and neural ODEs. Yeah, neural ODEs, probably that's what we've been talking about. Okay. Anyway, does someone has experience of what I just of with this stuff at all? Did what I just said make any sense whatsoever? Like, okay, I'll reiterate my points. Okay, so my guess of where this is going would be you have P initial on the right hand side, the original distribution, and you have P data on the left hand side. The transformation is unknown, but this defines a nonlinear functional equation for H, and H is equivalently defined by the vector field. The vector field is a neural network. So what you end up doing is that you want to satisfy this equation as much as possible. So that's why you're probably going to end up defining a sort of cost function, like a mean square error, based on left-hand side minus the left-hand side squared, some kind of integral or summation. You want to minimize that, and you do the gradient descent that way. I think it's better to start with discrete normalizing flow and then switch to continuous case. I don't even know what normalizing flow mean, right? Somebody mentioned it earlier, right? Let me just go check chat. Somebody even asked me, are you going to cover that? Because I had no idea. Christian is doing a fantastic job of being a spokesperson of mine when I was not reading chat. Indeed, I have zero clue of what is happening. Oh, the cat is so... Oh, the cat jumped on me. Because I've been ignoring her. She's rubbing me like crazy, man. All right, so I think the details of this, a detail of this business should be here. No? Should be like chapter 5, flow-based perspective, normalizing flows and neural ODEs, flow matching framework. Let's go here. So the flow matching framework, you want to learn a continuous time flow, either stochastic or deterministic, right? Here we're only considering the deterministic flow. It transports a simple Gaussian prior to a data-like sample from P data. Flow matching framework is built on this idea of a generalizer to learn a flow between two arbitrary fixed endpoint distribution, a source distribution and a target distribution, both assumed to be easy to sample from. Okay. Yeah, this is kind of like the picture I just drew. Okay, some fancier math. Fokker-Planck ODE or something, or sorry, PF Fokker-Planck equation. That's the PDE. You gotta. So this is some kind of expected square error. With I think, okay, with the Fokker-Planck equation. All right. Okay, so I think we're kind of on the right track, huh? We're kind of like on the right track because, even for ODEs, there's a Fokker-Planck equation. Even for ODEs, there's a Fokker-Planck equation known as the Liouville's equation in classical mechanics. Because you can think about, say, the evolution of density, or the evolution of a set of initial conditions. So how does say, a set of initial conditions change according to an ODE? The ODE defines a flow. Think of this as a blob of ink or something. There's no diffusion. It's just pure deterministic flow. How does the set of initial condition change? Oh my goodness, the cat is so sweet, man. Oh, she's purring on my legs. My goodness, how can I even work? All right. So more chat stuff. Normalizing flows has two cases. First one, discrete continuous case is more advanced. Continuous normalizing flow, newer ODEs. Flow matching all continuous case. Discrete normalizing case is much simpler to understand. Well, aren't we doing discrete? I mean, I don't know what I'm talking about. Aren't we doing discrete case by using the Euler's method? All right, anyway, perhaps that's not a correct understanding at all. Okay, but basically, I think at this point we're conceptually ready to look at diffusion model. All right, so diffusion model. Here we'll actually just do a very quick recap of what Brownian motion is and a stochastic differential equation is, because the details of that would take us like another few hours, which we already did in one of the previous live stream. I apologize if this is completely new to you, okay? Because SDE is a big topic, right? And to even understand the definition of SDE requires an understanding of stochastic integrals, right? So for that reason, I'm going to quickly go over this stuff, and because the goal is to reach at least the definition of a diffusion model by 12 a.m. Okay. Anyway, so earlier we considered the flow governed by deterministic dynamical system, an ODE. And here you're considering a stochastic analog, a stochastic extension of it, basically, right? So instead of having a deterministic flow, right? In a deterministic flow, given the current position and time, you know the tangent vector exactly, which is not the case in the SDE model, right? You know there's a deterministic component of it, of the tangent vector, but there's also a noise term. That's the basic idea of SDE. You perturb the vector field by a random noise. And the solution as a result is a stochastic process. This is, of course, much more complicated than the trajectory in a deterministic case. Right? Typically, such a trajectory is nowhere differentiable. Right? If the driving force, the noise term is driven by Gaussian, not Gaussian, but rather Brownian motion, which is defined here. All right. So here it says, SDEs extend the deterministic trajectory from ODEs with stochastic trajectories. A stochastic trajectory is commonly called a stochastic process, xt, x of t, and still you have t being from 0 to 1 and is given by the following. X of t is a random variable for every t. Okay, and and t from x of t is a random trajectory. Like, fair enough. Like, here's a stock chart, right? So basically, that's a stochastic process. We don't need to be super formal about the definition of a stochastic process here. So, in particular, when we simulate the same stochastic process twice, we might get different outcomes because the dynamics are designed to be random. Yeah, totally understandable.
Brownian motion. SDEs are constructed via Brownian motion, a fundamental stochastic process that came out of the study of physical diffusion process. You can think of Brownian motion as a continuous random walk, okay, which we also had a separate video on it. Diffusion, Brownian motion, Einstein. I think that's the latest episode of the stochastic calculus series. All right, so basically you can look at more details in our stochastic calculus series and also introduction to SDE series. Okay, it's introduction to SDE, not series, but just one episode now. Okay, you can easily find it on the channel. Let us define it. All right, a Brownian motion. This is a Brownian motion with t being less than or equal to 1. Okay, so but other than that is the standard definition of Brownian motion. We know that the initial condition is 0. Okay, know that the initial condition is 0. The trajectories are continuous from t to wt. The sample paths are continuous. Okay, and the two following conditions hold. Okay, the following conditions actually. Hang on, this is a d-dimensional Brownian motion actually. This is a d-dimensional Brownian motion because the increment follows a Gaussian distribution with 0 mean, and the d-dimensional identity matrix times the time interval length t minus s. Okay, so that's the central characteristics. That's the central one of the two central characteristics of Brownian motion. The variance is proportional to the length of time. And we mentioned multiple times on this channel that this is the sole reason that stochastic calculus is even needed. Because, not because of randomness per se, but because of this scaling law of the variance, linear being linear in time, makes the sample path sufficiently rough that standard calculus breaks down. Standard calculus, like the chain rule, okay, the product rule, the fundamental theorem of calculus, all those good stuff you know from regular calculus, only works for sufficiently smooth functions. And because of the Brownian motion is nowhere differentiable, and in particular in a way that is given by this scaling law of the variance, all right, stochastic calculus is needed because of it. Right? So that's the first condition. Right? For more details, check out the stochastic calculus series. Independent increment. Right? Independent increment, it basically means if the time intervals aren't overlapping, or with an overlap that has a measure of 0, right, then the increments over these time intervals are independent random variables. Independent Gaussian random variables in particular. Right. And this is the definition of Brownian motion. Is also called a Wiener process, which is typically denoted as a W. Simulation is very easy because you can use these two properties. You can start from the initial position, which is 0, and at each time step, you're going to add an increment. The increment is going to be Gaussian. And here you just simply sample a standard Gaussian, epsilon t, and gets multiplied by the square root of h. Remember, a square root of h times epsilon t will have a variance of h times id. Right, so that's the simulation of Brownian motion, which we'll also cover in the SDE series, in SDE live stream. So basically, you can simulate Wiener process extremely easily. This is all well-known method. Okay, so you can just follow the definition of Brownian motion to get this update formula for simulation. And here we have some sample trajectories of Brownian motion, which, as you can see, are extremely rough. They appear to be nowhere differentiable, and they are indeed nowhere differentiable. And for dimension d equals 1. All right. Brownian motion is as central to the study of stochastic process as Gaussian distribution as to the study of probability distribution. Okay, fair enough. That's, I guess, from an applied point of view, you can say that.
From finance to statistical physics to epidemiology, the study of random motion has far-reaching applications beyond machine learning. Sure. In finance, blah, 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 you can use to model the price of complex financial instrument. Black-Scholes video / live stream coming up. Also, just as a mathematical construction, random motion is fascinating. Yeah, it has many interesting properties. It's continuous, but nowhere differentiable. It's infinitely long. Well, it's nowhere differentiable, and as a result, more specifically, the derivative blows up everywhere. Therefore, the length blows up. Right. So it also has this fractal property. If you zoom in, it looks exactly like the same as you look at it from a distance. This is a fractal property, self-similarity. Anyway, these are all interesting topic on its own, but here this is what we're getting to. Okay, we want the stochastic analog to the flow model. We want a stochastic analog to this. All right, so how do we do that? So let's say we first need to define the SDE. The idea of SDE is to extend ODE by adding stochastic dynamics driven by Brownian motion. Because everything is stochastic, we may no longer take derivative. Well, that's actually not exactly very precise, isn't it? The reason you aren't, well, this is perhaps a little bit technical, but this is actually not very careful wording. Because being stochastic is not the reason that derivatives don't exist. It's because of roughness. Even for rough deterministic function, you can fail. Standard calculus can still fail. But anyway, this is the fine point, and on which we made a separate video on. That's fine. I mean, I would just try to emphasize that again. Okay, the reason that derivatives don't always exist here, is because of the scaling law. And such scaling law can totally happen even for deterministic function. Okay, it's not because of randomness. Okay, anyway, let's continue. So we need to find an equivalent formulation for ODE that does not use derivatives. Sure, yes, we do. We do, all right. So, okay, you can... Okay, so this is the reformulation of ODE in terms of remainders. So basically, here on the left-hand side, you have the definition of derivative. Right? And because it's a finite difference, you don't have the vector field exactly, but instead you have a remainder on the right-hand side. And just multiply by h, and this is what you get. Right? So this is a completely equivalent formulation of the ODE. It's still deterministic. Okay, still deterministic, but now you can add a stochastic term. And here, this is interpreted as an Ito SD, I believe. It should be an Ito SD, but I mean, without. Typically, overwhelmingly speaking, okay, unless specified otherwise, the SD is interpreted in the Ito sense. So, in the integral, this is the same as xt minus x naught, integrated SD on both sides. You get the integral from 0 to t, us x of s ds. This is just a Riemann integral from calculus, and the next integral will be from 0 to t sigma s dws, and this is Ito. Right, this is Ito. So, unfortunately, SD do not have a flow map anymore. Exactly. Right, exactly, because remember, what's the flow? A flow is a diffeomorphism from RD to RD, right? It's a purely deterministic map. Of course, because of randomness, we don't know, right? We don't have a invertible transformation anymore. Let me go get the cat. Cat is having a fight again. Oh, Jack. All right, I'm back. So basically, that's the SDE in a nutshell. Okay, you need the notion of Ito integral. I hope this is Ito integral. I hope this is Ito integral. Anyway, let's continue. But basically, you don't have the flow map anymore. You don't have the flow. Still, in the same way for ODE, you have the existence uniqueness theorem. Still, you have the existence uniqueness theorem. Basically, you have in the SDE, okay, we have this interpretation. The first term is known as a drift or deterministic movement. The differentiability of diffeomorphism being relaxed among, well, it doesn't even have a flow. It doesn't even have a flow, right? Well, it's not just the differentiability part. It's just that phi of the flow map needs to be invertible. And because of randomness, you don't know where you came from. Right? Like this. Here, let's say, oh, the final condition is this. Do I know the initial condition? Well, here, I mean, of course, every initial condition is given as w equals 1. But if you let's say if you revert the process backward, you don't know where you came from. So it's not even invertible, right, due to randomness. So basically, you don't even have a notion of a flow anymore. It's not just the smoothness that matters. But basically, here, in the SDE, the intuition is that the increment over an infinitesimal time interval has two contributions. One is drift, and the other is diffusion, or fluctuation, or noise, random noise. All right? And so to interpret this SDE, you can integrate. And the drift term give rise to an ordinary Riemann integral. Okay, give rise to an ordinary Riemann integral, which is no problem. And the second integral, the noise term, actually, is where things get tricky. Right? This is a stochastic integral with respect to the Brownian motion. And as it turns out, it behaves very differently from the Riemann integral because it's this on its own is ambiguous. This on its own is ambiguous. This is explained in detail in the intro to SDE series because the choice of sample point in a partition, because when you do integral, you partition the interval 0 to t into a bunch of subintervals, and you select sample points. You select sample points over those subintervals, and you compute a finite sum, take the limit, right? Take the limit so that the partition mesh tends to 0. Hopefully, the result converges and is independent of the choice of the sample points. I know that's a lot of information, but you can all find detailed explanation in the SDE live stream. All right? So, as it turns out that for stochastic integral with respect to the Brownian motion, that's not the case at all, because the sample point location matters. For different choice of sample location, you get different stochastic integrals. And for Ito integral, the sample point is chosen to be the left endpoint of the subinterval, and that's the definition of Ito integral. All right, so we'll just interpret. Okay, just going to interpret the SDE in the Ito sense. It's not indicated here. Actually, it is here because you see, the function sigma t is evaluated at time t, not t plus h. This is already indication of an Ito integral. Here, this is Ito. Okay, so we're correct. So we are correct in identifying the stochastic differential equation to be equivalent to an Ito integral. Right. Okay, so basically that's SDE. So if this was a stochastic calculus class, we would spend several lectures proving this theorem and constructing SDE with a full mathematical rigor, constructing a Brownian motion from first principles, and constructing the process xt via stochastic integration.
Perhaps we'll do a video on that. Perhaps not like like with full mathematical rigor, but we can still show the fundamental ideas of showing existence and uniqueness of SD. Perhaps we should do that, just to have some understanding in, say, the qualitative aspect of differential equations. Okay, so we should probably do that at some point. But this is a machine learning class, right? This is a machine learning course. We're not going to do that. So we know that every ODE is also an SD, right? Of course, if you set the noise term, set the sigma function to be 0, then the noise term gets killed. This way, the SDE degenerates into an ODE. Nothing surprising here. When we speak about SD, we consider ODE as a special case. The diffusion coefficient sigma t equals 0. Okay, so that's basically the situation. Okay, and an important example is the Ornstein-Uhlenbeck process. Ornstein-Uhlenbeck process is discussed and introduced with physical background in the second episode of the series Stochastic Processes for Physicists. Okay, basically, in a nutshell, this SDE models the velocity distribution of Brownian motion. Okay, and this is, as you can see, this is also a natural generalization of the exponential decay model. In the exponential decay model, ODE, okay, you have xt dot equals minus zeta xt. But now you just add a noise term. The noise term will have a constant volatility or diffusion coefficient sigma, and dxt is minus zeta x of t dt plus sigma dwt. So this is the linear differential equation. The linear differential equation, and the result is actually very simple. The solution is actually very beautiful, because the integral, right? Looking at the integral version of it, the integral here is the integral of constant sigma times dw. That's a Gaussian. This is a linear combination of Gaussian. And as a result, x of t is also Gaussian. So if it is a Gaussian, then it all just boils down to finding the mean and variance of the distribution. Okay, so this will be perhaps, should I do that here because I don't have time? Okay, so the solution to this ODE, to this ODE, also known as the Ornstein-Uhlenbeck process. Ornstein-Uhlenbeck process is also a Gaussian distribution because of linearity, because this is a linear ODE, a linear SD, linear in X. So that's why the result is still a Gaussian, and actually it converges to a stationary distribution. It converges to a stationary distribution. It's a Gaussian distribution with 0 mean and sigma squared over 2 zeta. That's the SDE here. This is the SDE. Well, I mean, to derive this, we need a separate live stream on, or video on SDE. I need a new episode for the SDE. Okay, yeah. The visualization would be this. The visualization would be this. Okay. The initial starting point, let's suppose this is given at different values. As you can see, it roughly behaves like an exponential decay curve, but with some fluctuation along the way. And as you can see, with bigger sigma values, this is sigma equals 0.25, this is sigma equals 0.5, and this is sigma equals 1, the roughness increases.
the deviation, the fluctuation from the exponential decay curve grows. It grows. Right? And as a result, it won't just settle down to the equilibrium position like in the ODE case. It won't happen, right? Because we know from the exponential decay model in ODE, the asymptotic behavior of x of t is just it tends to 0 as t tends to infinity. That's not very interesting. In the diffusion case, in the diffusion model, sorry, not diffusion model, but in the SDE, as t tends to 0, the distribution of xt settles down, not xt itself. As you can see, for large t, x of t is still random. There's still fluctuation. But the spread pretty much stabilizes. The spread, the distribution itself pretty much stabilizes. It becomes stationary. The distribution becomes stationary. Right, so that's the idea of a stationary distribution, which is also, if you've seen some Markov chain, it's the same idea, but it's just continuous time and continuous state space. All right, so in this scenario here, it is said that the distribution, the stationary distribution, right? And of course, to derive this, we need, as I said, you need a separate session on SDEs. The idea is it settles down to a Gaussian distribution, and the Gaussian distribution is 0 mean and sigma and the variance sigma squared over 2 zeta. Sigma squared over 2 zeta. And as you can see, if zeta is a constant, the larger the sigma value is, the greater the spread in a Gaussian distribution, which is exactly what these visualizations show, which is completely intuitive, right? The bigger the noise, the more spread out the stationary distribution, or just the more spread out the trajectories in general from the exponential decay model. All right, so that's a simple, ridiculously simple, yet, yeah, this is a ridiculously short introduction to SDE. And ODE was noise. And the simulation of SDE is exactly the same as you expected, the Euler's method. It's called the Euler-Maruyama method. It's essentially an SDE. What the Euler's method to ODE. So instead of just having this term right here, that's the standard Euler's method, you're adding a noise term. Remember how you simulate Brownian motion? You just Wt plus this noise, the increment, square root of h times epsilon of t. Right? Right. So the increment is of order square root of h. Okay. The time interval is of length h, and the added increment is of order square root of h. And here it's the same thing. The deterministic growth, deterministic increment is of order little h because of Euler's method. And also, but the noise term would have an order of a square root of h. So we know for small h, the randomness dominates. H is meant to be very small. A step size is meant to be very small. So the overwhelming influence in this update should be random fluctuation. Because remember, when h is small, square root of h is much larger than h. When h is much less than 1, greater than 0, square root of h is much greater than h. Right? Just for example, look at h equals 0.01. The square root of h would be 0.1, which is 10 times h itself. Right? So you will be simulating SDEs using the labs, and usually stick to the Euler-Maruyama method. You see, this is extremely extremely straightforward. Right? If you understand the definition of SDE and you know Euler's method, boom, you know Euler-Maruyama method. Of course, just like in the theory for simulating ODEs, there are much better, much more advanced methods for simulating SDEs, but we're not getting into that. Right? This is just the most straightforward method for simulating an SDE purely from its definition. Okay, and this is also how we introduce the Ito SDE. Okay, so now this is as we did earlier, right? We had a self-contained introduction to ODE, and this is an extremely short introduction to SDE. For more details, see the Introduction to SDE live stream. We're now ready to give the definition of a diffusion model. So for diffusion model, what do we want? Well, we kind of want the same thing according to this note here. Right, remember, what's our main objective in the flow matching, flow-based model? Right, the ultimate goal is to sample from P data. The ultimate goal is to sample from P data. So how can we do that, right? The flow model tells us, well, you pick an initial distribution, right? You pick an initial distribution, you're going to tweak the flow so that the transform distribution of the initial distribution matches P data. You're going to tweak the flow. And by tweaking the flow, it is equivalent to tweak the vector field. The vector field is represented by a neural net. Right? So here, I mean, we lost the notion of a flow, but the notion of time evolution still exists. Right? It's just that the vector field has a random noise term in it. Okay, so I think we're doing essentially the same thing, right? Because, you know, there's no loss here. Even in a flow method, there's no direct reference to the flow. The flow is represented by the vector field. And the vector field, well, now just have a noise term, and you can pretty much generalize it verbatim. So let's see if that's the actual correct understanding. We can now construct a generated model via an SDE in the same way as we did for ODEs. Remember that our goal was to convert or transform, right? Convert or transform a simple distribution P initial to a complex distribution P data. Like for ODEs, the simulation for an SDE is randomly initialized with, okay, X naught follows P initial. It's the same business. It's a natural choice for this transformation. Okay, to parameterize this SDE, we can simply parameterize its central gradient, its central ingredient, the vector field UT via neural network. So this is the neural ODE once again, right? You remember in the SDE is the drift. It's a purely deterministic function. Well, sigma is also deterministic, right? So you're going to parameterize the vector field U exactly the same way as earlier, using a neural net. The U is a neural net. Vector field UT is a neural net. All right? And you do the Euler-Maruyama method instead of Euler's method. Let's check the details here. You have the neural network, like in algorithm 1, number of steps, diffusion coefficient. These are all given. All right, so these are all given, and you just do the time evolution, discrete time evolution forward in time. And it's completely analogous. Okay, if you understand the Euler's method, you understand this. Of course, if you understand the Euler's method and you understand the definition of SDE, then this almost falls out immediately, as if you can independently discover it yourself. Okay, so the definition of diffusion model is as follows. Diffusion model here, this is the definition here. The diffusion model is that you have random initialization, and the time evolution is described by an SDE. And yeah, that will be it. That's the diffusion model. Right? And I suppose that the goal is to still make x1 follows p data. Okay, let's summarize that. In algorithm 2, we describe the procedure by which to sample from a diffusion model with the Euler-Maruyama method. We summarize the result of this section as follows. All right, throughout this document, the diffusion model consists of a neural network, u theta t. That's a vector field with parameters theta that parameterizes the vector field and a fixed diffusion coefficient. Hang on, what do you mean by fixed? So the diffusion coefficient there's no parameter in it. Right? This might be time dependent, but you do not need to tweak the diffusion coefficient. Right? You see, the neural net is for the drift only. Here, this is the SDE, this is the deterministic increment, and this is the random noise. The coefficient u in the drift term depends on the parameter, that's a neural net, and sigma t is fixed. Fixed in the sense that you do not need to tweak it. Right? You don't need to. There's no need to parameterize the diffusion coefficient. It is a given function of t and x. Okay, that's the diffusion coefficient. All right, so that's why here we have the following setup. You have the neural network for the drift, for the diffusion, whatever you want to call it. Okay, same business as earlier, same in the flow model, and you have a fixed diffusion coefficient. Right, a fixed diffusion coefficient. Interesting, actually here it's not even dependent on x, huh? Sigma t is not even a function of x. Sigma t apparently is just a function from 0 to 1 to 0 to infinity. You see, sigma t is a deterministic function at time. It doesn't even depend on the state x. That's interesting. Actually, I'm not quite sure about that. I think theoretically it should also depend on x of t, because this is too restrictive. I don't know. Okay, but let's just keep an eye on it. Okay, perhaps in the future sigma can also depend on x. Like there's also a simple SDE called the geometric Brownian motion. Right. The geometric Brownian motion here, the noise term would be sigma, a constant sigma times x. It's used for modeling an asset prices. The geometric Brownian motion, one of the fundamental assumptions behind the Black-Scholes model. Anyway, so here, but basically the main point is that the neural network is only used for the drift, but not for the diffusion coefficient. Right, so that's the main point. To obtain samples from our SDE models, i.e. to generate object, the procedure is as follows. First, you initialize. Right? Initialize, for example, say P initial is a Gaussian. It's simple, like a spherical Gaussian. And you simulate the SDE using the Euler-Maruyama method. Very straightforward stuff. And the goal is that you want to make x1, you have distribution P data. The diffusion model with sigma t equals 0 is called a flow model. Okay, so yeah, we managed to give a definition of a diffusion model we started from 7, so the 4.5 hour. It shouldn't be too bad. So that's a diffusion model. Let's try to perhaps give a more in-depth description of it in the remaining half an hour. So let's do that. Okay, so this is a diffusion model. I think, yeah, you don't need to even change the visualization that much. You lose the notion of a flow, right? You no longer have the notion of diffeomorphism. But the idea that the initial distribution evolves, the initial distribution evolves over time, and hopefully you will get and hopefully you can make Okay, the final distribution, the same as p data. It's the same idea. It's just that the dynamics is now stochastic. Is no longer an ODE but an SDE. Okay, and actually, guys, Fokker-Planck equation describes how the distribution changes over time. That's exactly, I mean, if you've seen the Fokker-Planck episode that we did a week ago, the Fokker-Planck equation is exactly the PD that governs the time evolution of the distribution. So in that case, all right, so in that case, we have the initial condition and the final condition, and then you have a PDE. What do you want? It's like almost like solving a boundary value problem, huh? I don't know. Okay, but anyway, let's continue, right? So it's not specified here. It's not specified how can you make sure that x1 follows p data. I guess that's what we're going to investigate. So solving the SDE is done at each iteration in a sequence. And the sequence u theta k underscore t underscore k in big N. So u is, yeah, you see the iteration is this one. U is, so yeah, you basically, u theta t is given. This is a function of x. This is a function of x, all right? The SDE is solved by, approximately, of course, by this update rule, Euler-Maruyama method, right? This is just Euler's method. And this is a random perturbation. Sigma t times square root of h times epsilon. Is that clear? This is solving the SDE numerically. Euler-Maruyama method. U is a neural network that represents a vector field. Are we clear about that? Right. Okay. Anyway. So now we have the so-called flow matching problem. Let's look at this one. Perhaps we can finish reading this part and we will call it a day. Can we do so? Perhaps that's not quite realistic because there's proof in here. Okay. But that's fine. We can still try to do as much as possible. Okay, pretty cool. Okay, so that's more math is coming. Okay, so basically we want to do what? So what is flow matching? Is this a simulation problem or a estimation problem? Remember, in our first set of notes, there are two. Oh, the cat. Okay. All right. All right. So, I guess we'll try to answer one question here. Well, that looks like it's solving the SDE versus how the solution is used in larger context. Yeah, I mean, Euler-Maruyama method is a very general method for solving SDE. It doesn't needs to. It's not just specific to artificial intelligence, right? You can simulate all sorts of SDEs in different applications using the Euler-Maruyama method. It's just like the Euler's method for ODEs. You can use it for whatever application when there's an ODE, right? So here, I mean, I'm trying to accomplish one thing in the next half an hour, perhaps more. That is to say, I want to know what flow matching is about. Does it belong to this part, the learning/inference or estimation step, or the simulation step? Let's try to understand that. In the previous section, we constructed flow and diffusion models as generative models parameterized by a neural network vector field. Cool. However, we have not yet discussed how to train them exactly, i.e. how to optimize the parameters theta such that the generative model returns something sensible. For example, a nice looking image or exciting video. Next, we discuss flow matching, an algorithm that trains U theta t that is simple, scalable, and represents the current state of art. Right. Remember, like how I explained it, or should be understood it in this little setup, right? So imagine you have the flow. In the flow definition, right, ODE scenario, the flow is this transformation H, and you want to find an H that transforms the initial distribution into the target distribution, or the P data. Okay? So this relation defines a nonlinear equation, nonlinear functional equation for the flow, which is highly complicated. The flow is equivalent to the vector field. The vector field is parameterized by a neural net. So what you can perhaps do is to minimize the error in between the left-hand side and the right-hand side, and you do a gradient descent of some sort. So that was my original intuition, but perhaps you can achieve the similar goal. Okay, you can achieve the same goal of basically trying to calculate the approximate flow or the approximate vector field, same thing, through some other criteria. Perhaps you can do so. Okay, but let's just figure out what the note says. All right. In this section, we restrict ourselves to flow models, i.e., we have an ODE. Okay, we have a neural network U theta t and obtain samples from the generative model by simulating the ODE. That's simulating the ODE. We've seen that. And use the endpoint x1, 4, this is probably 4, for t equals 1 as samples. As we discussed, our goal is that x1 is distributed according to the data distribution p data, i.e. x1 follows p data. Therefore, the question how to train a neural network is really the following question. How do we optimize data such that simulating the flow model in equation 10 results? Basically, how do you exactly, right? We've been saying this in various different ways. Is how do you train the ODE? You want to train the ODE so that for the initial distribution of choice, you can reach the data distribution that you want. Okay? How do you optimize data so that simulating the flow model in equation 10 results in a sample from the data distribution x1 follows p data? All right. Well, p initial is pure noise. P initial is just a most commonly is just a random. It's just a standard Gaussian. So let's take a look at this picture here, this little visualization. We want the data distribution to represent, we want the data distribution to represent hand-drawn, handwritten digits. All right? And the initial distribution is pure noise. There's no visible pattern at all. Right? So you want to design a flow that maps this distribution to this distribution. So that's basically what we're trying to get to. Figure 4, gradual interpolation from noise to data via Gaussian conditional probability path. Actually, we don't know We haven't seen that. Okay. For a collection of images, note that each image is data point of dimension 32 times 32. All right. So in plotting individual samples from the probability path, okay, so we have to define what a probability path is. While in figure 5, we plot the distribution of it as a 2D diagram. What's figure 5? Oh, that's distribution. That's the distribution. Anyway, initially it's pure randomness, spherical Gaussian. And the conditional distribution becomes a star, and the marginal distribution becomes a lattice. Well, what is that? That's so interesting. How does this becomes like a chessboard, huh? But anyway, okay. So at least I think we're clear with one thing. Right? At least we're clear with one thing. Our initial understanding, I was kind of in shock when the section on flow model ended here. Right? I was like, oh, how can you make sure that X1 actually follows P data? There's no guarantee, right? Here we're actually doing that problem, right? That's the training step. That's the training step. So once you have, let's say, a trained model, right? So at least in algorithm 1, once you already have the trained U, simulation is very simple, right? Once you already have it's just a simple Euler's method. That's actually very simple. So of course the point is now, let's get back to the new section here. There's, I think, a few new notions that needs to be defined. Let's see that. All right. Conditional and marginal probability path. The first step of flow matching is to specify a probability path. Intuitively, a probability path specifies as a gradual interpolation, or evolution, right? Evolution between the noise, P initial, and P data. So you want to somehow design an algorithm that turns this to this. So that's P initial, that's what you already know, and this is P data, which we also know. Okay. But how do we do that? But why would we want? Why is obvious, right? You want to sample from P data. The why is obvious, right? Remember that our desired ODE trajectory fulfills X naught follows P initial for T equals 0, and X1 follows P data for T equals 1. Right? We know that. Right? We know that. But what about time in between? Right? So it's almost like a boundary value problem, but except now the boundaries are two distributions instead of, two numbers. Almost like a boundary value problem for ODE. You have the two distributions, P initial and P data. Right. But what about points from 0 to 1, in between start and end? It turns out that we have some freedom to choose what could happen in between. That is mathematically formalized in probability path. So basically, the probability path is just a parameterized distribution. So that when the parameter t equals 0, you have the initial distribution, and when the parameter t equals 1, you have the final distribution. And in the middle, it looks like something like this. It's a process of gradually turning noise into pattern. That's basically intuitively what's a probability path. It's the evolution of probability distribution, turning from P initial to P data. So that's a continuum of probability densities. All right. So in the following,
for a data point z in Rd, we denote delta z, the direct delta distribution. Of course, this is a classic direct delta function in physics and distribution theory. Right? So it's just represent a distribution that is degenerate, that is concentrated at the point z. This is simply a distribution one can imagine. Sampling from delta z always returns z. It is completely deterministic. A conditional interpolating probability path is a set of distributions pt of x given z over Rd such that what? Such that the initial distribution, this is 0, when t is 0, you get the p initial. Why gradual interpolation rather than direct mapping from p initial? It is a, I mean, why gradual? Okay, you said, why do you need to consider a continuum that goes from here to here, right? Like, why do we need this intermediate stuff? Because remember, the way you go from here to here is by solving ODE, is by using the Euler's method. And the whole reason you need Euler's method is because you don't have an analytic formula. You don't have an analytic formula. So basically, you don't have an analytic formula of the flow as a function of the initial value, right? So let's just say, I mean, for the simplest scenario, like this one here, like the exponential decay model, this is the formula for the flow. Given t and x naught, you can calculate the target or the value psi 1 of x naught in one go explicitly. It's just e to the minus theta times x naught. Of course, you do not need intermediate values in that. This is just explicit value. But in most circumstances, of course, it's impossible. You need to do it step by step. And that's why you need a vector. Essentially, you need the vector field u at each time step, which is equivalent of knowing the flow at each time step, which is equivalent of knowing these intermediate probability distributions. Does that make any sense? Because if you have the analytic formula of the flow, then of course you don't need the closed form formula for the flow. Of course you don't need these intermediate values. And because we can only do so realistically using Euler's method, that means you need, well, the value of the vector field at intermediate time step, which is equivalent of knowing the flow at intermediate time step, which is equivalent of knowing the intermediate distributions. All right, so yeah, so that's why you need interpolation. Okay, interpolation rather than direct mapping, because direct mapping is in almost all circumstances, except for extremely simple situations, impossible to find. All right, so here we need the probability path to satisfy the following two conditions. Okay? When t equals 0, you get the initial distribution. Right, you get the initial distribution, and when t equals 1, you get delta z. You get delta z. This is rather interesting. This looks like a backward evolution, because in the theory of stochastic process, typically the initial value is known, right? Like here, in a distribution, or in a definition of Wiener process, for example, the initial value is given. W naught equals 0. So that means the initial distribution is a degenerate distribution at x equals 0.
Can you see? Can you use optimal transport here to have a geodesic between p initial to p data? Yeah. Yeah. So this is an extremely good question. I do not know. Okay, I do not know because here, I mean, in the nodes, we're only considering flow-based model and diffusion model. Remember, as I said earlier, I'm still very new to generative AI in general. Right, so basically, like a chat, this person mentioned an extremely powerful and valid point. So, what's optimal transport? It's like you want to move a pile of sand from one shape to another that minimizes some cost function. That's optimal transport. That's optimal transport. So basically, it's very similar to moving one probability distribution to another probability distribution, right? From P initial to P final. It's the same problem. It's not just similar, it's the same problem. Right? And what we're doing, I mean, we still don't know how to train it yet. Transport. Is there a picture somehow? Yeah, you want to turn one pile of sand into a different shape. And in a process, you want to minimize some cost function. And this was originally considered by French mathematician Monge. Right? He was actually a military engineer in the French army, and at the time they were building fortresses, so they want to move stones, rock basically, from one place to another into the shape of a fortress with minimal energy, in a way, minimal cost, whatever you want to call it. And here we're kind of doing the same, right? We're trying to transport the initial distribution to the target distribution or data distribution. While at the same time, you want to do it like as efficiently as possible, right? Yeah. But remember what we're trying to do, right? Remember what we're trying to do. We are trying to simulate data point. We are trying to simulate data points. So here, we're trying to simulate data points in this distribution, in P initial. Yeah, I think optimal transport could be a useful concept here. Glad to see people glad to see folks to go fast from P initial to P data. Not quite sure what that means. Okay, but basically, I mean, the idea of optimal transport can certainly be intuitively be quite appealing. Actually, I don't know. Okay, I don't know. Maybe let's say actually, guys, I'll just do a quick search here. Is optimal transport even show up? Optimal transport. Not here. Okay, not here. Perhaps not in the context, but perhaps not in the context of, say, diffusion and flow model. Probably not, because we can't find the keyword here. But I think it's a very solid direction. It's a very solid direction, but perhaps just not here. All right. Okay. So what we define is a conditional probability path. It goes from the initial distribution to a single delta, to a single data point. But this is like backward diffusion, huh? It's like backward diffusion. It's like in a diffusion, in a Gaussian distribution, in the diffusion, right here we are described earlier in the winner process, the initial condition is given. So the initial distribution is a single delta at 0. And as time evolves, it becomes a Gaussian. Okay. The distribution of x of t at any time t is a Gaussian distribution, and the mean stays at 0 and the variance increases in t. But now here, it seems like we're defining the conditional probability path as some sort of backward diffusion. Right? At the final point, you have a single delta, whereas the initial distribution is some arbitrary distribution. In other words, the conditional probability path gradually converts the initial distribution into a single data point. Right? You can think of a probability path as a trajectory of the space of distribution. In the space of distribution, yeah, it is a trajectory, indeed. All right. So anyway, we'll come back to these pictures later, but let's continue reading. So what is going on here? How is this helpful? Well, every conditional probability path induces a marginal probability path. Okay? A marginal probability path, because if you don't care about z, right, if you don't care about z, you only care about x, that's a marginal probability path. Every conditional probability path. How do you get, for that you must need the distribution of z, right? Yeah. It's defined as a distribution that we obtain first by sampling a data point z from p data, yeah, and then sampling from the conditional distribution. So basically, you have two equivalent ways. You have two equivalent ways of generating x from pt. Oh no. This is one single equation. So basically, what happens is that you can generate z from p data. Right? Suppose you can do that. After all, p data is known. If you know p data, you can simulate it, generate z, and conditioning on z, you're going to generate x according to the conditional distribution, right? So this is remember, the conditional probability path. Pt of dot given z is this distribution here, right? The two endpoints are known, and in the middle, suppose this is well defined, I guess. It hasn't shown that yet, but suppose this is conditional. Sorry, this is a conditional. It doesn't say the conditional, right? So there's probably multiple paths. There's no guarantee that this is unique, okay? But basically, you have this conditional probability path, and if you have that, you can generate the marginal path. The density of the marginal path is the standard formula for the density of the marginal distribution, right? Conditional distribution times the probability of condition, and then integrate the nuisance variable that you don't care about, z. Note that we know how to sample from pt, but we don't know the density value of pt, as the integral is intractable here. We can actually compute equation 12, but not equation 13. Yeah. So because this integral is ridiculously high dimensional, remember dz. What is z? Z comes from rd. So this is in this silly little example, d is 32 times 32. So this is something like a multiple integral with 900 plus integral signs in it. Virtually impossible to calculate, but this is doable. Here, this is doable if you know the if you know the target distribution, and if you know the conditional probability path. All right, so then you can simulate PT, because calculating the density of marginal paths is pretty much impossible. All right. The by far most important example of probability path is the Gaussian probability path. All right. We strongly recommend reading the next example thoroughly. Do we have time? No, we don't have time. Okay, we don't have time today. We don't have time today. All right. So I guess perhaps how do we train? Can I at least get some kind of definitive answer here? How do you train the you know, here's the question, right? Earlier we raised the question. How do we even train the neural vector field? Here, that's the question. Is there a summary for that? Because earlier we saw a summary in each section. There's a section, summary. Some proofs. We'll do that. Learning the marginal vector field. Okay, that's promising. There's a theorem. Okay, haven't read the details yet, but quite fascinating stuff, but okay, there's no summary, unfortunately. Okay, anyway, I don't think even if actually there is a summary. There is a summary here. Flow matching training consists of learning the marginal vector field, UT target. I thought you were talking about UT theta, but this is UT target. Fine, fair enough. To construct it, we choose a conditional probability path that fulfills this condition. Remember, P initial is just a Gaussian, right? Typically, is the spherical Gaussian, and you can interpolate a spherical Gaussian and a degenerate Gaussian. That shouldn't be too hard. You should be able to do that. And you can define a conditional vector field. Yes, conditional vector field such that its corresponding flow fulfills this goal. Yeah, that's exactly what we agreed upon. Or equivalently, that U satisfies the continuity equation, which is a PDE. The marginal vector field defined this way. So the marginal vector field satisfies the integral equation. The marginal vector field defined this way follows the marginal probability path. To learn it, we minimize the conditional. Yeah, so, well, eventually you will have to introduce some kind of objective function. And here the objective function, the conditional flow matching loss, LCFM, as a function of theta. Remember, theta is the parameter that parameterizes the neural vector field or the neural ODE. And you define this to be the expected value of, it's kind of a mean square error. This is basically like a mean square error. And you are assuming that T is uniform. So T is uniform. Okay, so T is integrated over, right? The T is integrated over. Z follows P data, so Z is integrated over. And X follows, okay. So at least we know what this means. At least we know what this means. All right, okay, but I mean, there's a bunch of proofs that we just skipped, so it won't be. It's. I mean, of course, I don't understand how this is obtained, but basically, because we skipped a bunch of proofs and examples, but at least now we know that our main complaint in the earlier section that, oh, we don't even know how you would get to the transformation, right, or the flow. turns out to be a quite significant part of the problem. Because if you already know the vector field, then sampling is ridiculously easy. Just the Euler's method. And things are just slightly more complicated in the SDE case because you just need to add an extra noise term. The hard part, of course, is how would you find the parameterized neural net? Right? How would you find the parameterized neural net so that the target distribution actually equals what you want? So perhaps we will do this another time. But anyway, guys, thank you very much for watching, and I'm getting very exhausted. And I'm very glad to be able to back to YouTube. And actually, today's live stream is a fantastic start. Already over 3,000 views, which is quite amazing. I suppose this is because the topic of diffusion model is very popular. It's very popular nowadays, and a lot of people want to understand the details of it. So thank you very much for tuning in. I'm very much a novice in this respect. Okay, I guess this is a highly interdisciplinary field, as we mentioned. It uses deep learning and also, of course, stochastic analysis, numerical methods, all kinds of interesting stuff. So I would love to hear your feedback. I mean, if you want, you can tell me, did I misunderstood something in specifically one aspect? It doesn't you don't need to be an expert or anything on this matter, but I know, for example, some people are more experienced with learning stuff, with more not learning as a personal individual activity, but deep learning, okay, as generative AI. Because I have very little experience in that. I do have some experience with numerical methods and stochastic process. So I guess we can all learn from each other, okay? And hopefully in the process we're making this subject, which is quite complicated, easier for other people to learn as well. Thank you guys very much for watching, and I'll see you guys